Imagine stepping into a world where colossal beasts ruled every corner of the earth. Picture towering predators with razor-sharp teeth longer than your hand, armored giants the size of school buses, and creatures so massive they could peer over four-story buildings. This was reality for 160 million years. But here's what most people don't know. The story of dinosaurs isn't just about T-Rex and Triceratops. It's an epic saga that spans nearly 200 million years, filled with catastrophic disasters, evolutionary arms races, and survival against impossible odds. From their humble beginnings as small bipedal creatures to their final moments when death rained from the sky, dinosaurs experienced triumphs and tragedies that would make any Hollywood blockbuster pale in comparison. What if I told you that before dinosaurs ever existed, our planet was dominated by creatures so bizarre they seem like something from an alien world? What if the rise of dinosaurs was actually triggered by the most devastating mass extinction in Earth's history? And what if their entire 160 million year reign was bookended by two apocalyptic events that reshaped life on our planet forever? Today, we're embarking on the complete journey through the age of dinosaurs. Not just their glory days, but their entire story, from beginning to end. We'll witness how a small group of survivors emerged from the ashes of global catastrophe to become the most successful animals that ever lived. We'll explore how they conquered land, sea, and sky, developing hunting strategies and defense mechanisms that were millions of years ahead of their time. But this isn't just another dinosaur documentary. We're going to uncover the dramatic events that shaped their world, the fierce competitions that drove their evolution, and the shocking truth about their final day on Earth. By the end of this journey, you'll understand not just what dinosaurs were, but why their story is perhaps the most incredible tale of survival, dominance, and ultimate tragedy in the history of life itself. Before we dive into the age of dinosaurs, we need to set the stage. Our story begins in a world that would be completely unrecognizable today. This was the Permian period, roughly 300 million years ago, and Earth looked nothing like the planet we know now. Picture a single, massive supercontinent called Pangaea, stretching across the globe. This colossal landmass was surrounded by an enormous ocean called Panthalassa. The climate was drastically different from anything we experience today. During the earlier Carboniferous period, the world had been warm and humid, covered in vast swamps and forests of giant ferns and club mosses. Trees grew to incredible sizes, with trunks reaching nearly 5 feet in diameter and heights of over 100 feet. Through the misty vapors of these ancient swamps, you might have glimpsed massive fungi called prototaxites, some growing taller than 2-story buildings. But as the Permian period progressed, everything changed. The formation of Pangaea dramatically altered the planet's climate systems. The interior of this supercontinent became increasingly arid, creating some of the largest desert regions in Earth's history. Meanwhile, the southern portions of Pangaea were locked in ice, with massive glaciers covering what would eventually become India, Australia, and South America. The oceans of this time were inhabited by creatures that seem like mythical beasts today. Swimming through these ancient seas was Helicoprion, a bizarre shark-like predator with a spiral whorl of teeth in its lower jaw. This dental spiral could reach 3 feet in diameter, creating one of the most unusual feeding mechanisms ever evolved. Despite its fearsome appearance, this creature primarily fed on soft-bodied prey like squid and small crustaceans. On land, the Permian world was dominated by an incredible diversity of life forms that preceded the dinosaurs. These weren't the massive reptiles we typically imagine, but rather a fascinating array of mammal-like reptiles and early archosaurs that would set the stage for everything that followed. One of the most successful predators of this era was Dimetrodon, a sail-backed reptile that has often been mistaken for a dinosaur, but actually lived millions of years before the first dinosaurs appeared. This 4-meter-long predator was equipped with sharp, serrated teeth perfect for tearing flesh. Its most distinctive feature was the enormous sail on its back, formed by elongated vertebrae covered with skin. This sail served multiple purposes: temperature regulation, display during mating rituals, and possibly even as a swimming aid. The sail gave Dimetrodon a crucial advantage in the hunt. While other reptiles needed hours to warm their bodies in the morning sun, Dimetrodon could be ready for action in just 80 minutes, thanks to its solar panel-like sail. This meant it could hunt in the early morning hours, when its prey was still sluggish and vulnerable. But Dimetrodon wasn't the only formidable predator of the Permian. Gorgonopsids stalked the landscape like prehistoric saber-toothed cats. These mammal-like reptiles had powerful builds, long saber-like canine teeth, and, remarkably, a third eye on top of their heads that functioned like a periscope for hunting. With well-developed brains and excellent coordination, they were perhaps the most dangerous predators of their time. These creatures employed sophisticated hunting strategies, using hit-and-run tactics to wear down their prey. They would attack, retreat, and attack again, gradually weakening their victims until they could deliver a fatal blow. Even the heavily armored herbivores of the time, with their thick, bony plates and defensive spikes, were not safe from these persistent hunters. Living alongside these apex predators were the early ancestors of mammals, small furry creatures called cynodonts. These dog-sized animals were warm-blooded and covered in fur, giving them the ability to remain active during the cooler hours when larger predators were less mobile. They lived in burrows and cared for their young, possibly even nursing them with milk. Their success lay in their adaptability and their ability to exploit niches that larger animals couldn't access. The plant eaters of the Permian were equally diverse and impressive. Massive herbivores like Esteminosuchus wandered the landscape, their skulls adorned with bizarre horn-like protrusions. These creatures had to constantly migrate in search of vegetation as the climate became increasingly arid. But perhaps the most significant inhabitants of the Permian world were the early archosaurs, the group that would eventually give rise to dinosaurs, crocodiles, and birds. These early forms were still relatively small and generalized, but they possessed key innovations that would prove crucial in the challenges ahead. They had more efficient respiratory systems, better temperature regulation, and more advanced locomotion than their contemporaries. As the Permian period progressed, competition for resources intensified. The increasingly arid climate meant that water sources became precious commodities, drawing diverse assemblages of animals to rivers and oases. These gathering spots became theaters for dramatic encounters between predators and prey, with massive crocodile-like predators lurking in the water while various herbivores came to drink. The diversity of life during the Permian was truly staggering. Insects had grown to enormous sizes due to high oxygen levels in the atmosphere. Dragonflies with 3-foot wingspans patrolled the skies, while millipede-like arthropods over 9 feet long crawled through the undergrowth. The higher oxygen content, reaching 35% compared to today's 21%, allowed these creatures to reach sizes that would be impossible in our current atmosphere. But this incredible world was living on borrowed time. Deep beneath the surface of Pangaea, massive geological forces were building toward one of the most catastrophic events in Earth's history. Tectonic plates continued their relentless movement, and volcanic activity was increasing across the globe. The stage was set for a disaster so complete, so devastating, that it would wipe out over 90% of marine species and 70% of terrestrial animals. This event, known as the Permian-Triassic Extinction or the Great Dying, would bring an end to the Permian world and create the conditions necessary for dinosaurs to rise to dominance. As we stand on the brink of this catastrophe, it's worth reflecting on the incredible diversity and complexity of life that had evolved by this point. The Permian world was a testament to evolution's creativity, filled with experimental body plans and ecological relationships that would never be seen again. The mammal-like reptiles had developed sophisticated behaviors, complex social structures, and advanced physiological adaptations. Yet none of this would be enough to save them from what was coming. The forces building beneath Pangaea were about to unleash devastation on a scale that dwarfs any natural disaster in recorded human history. Massive volcanic eruptions would poison the atmosphere, acid rains would fall from toxic skies, and temperatures would soar to lethal levels across much of the planet. But from this apocalypse would emerge opportunity. The few creatures that managed to survive would find themselves in a world suddenly empty of competitors, with vacant ecological niches waiting to be filled. Among these survivors were the ancestors of dinosaurs, small and seemingly insignificant creatures that possessed just the right combination of traits to endure the coming catastrophe. The extinction event that ended the Permian would be the crucible that forged the age of dinosaurs. In the aftermath of global devastation, these humble survivors would begin their remarkable journey toward becoming the most successful vertebrates in Earth's history. Their story of survival, adaptation, and ultimate dominance was about to begin. Born from the ashes of the greatest mass extinction our planet has ever known. As we prepare to witness this transformation, remember that the rise of dinosaurs wasn't inevitable or predetermined. It was the result of a perfect storm of catastrophic events, evolutionary innovations, and sheer chance that allowed these particular creatures to not just survive, but thrive in ways that would reshape life on Earth for the next 160 million years. The catastrophe that ended the Permian period began not with a bang, but with a rumble deep beneath the Earth's surface. Around 252 million years ago, massive tectonic forces were reshaping the newly formed supercontinent of Pangaea. As the enormous land masses of Laurasia and Gondwana continued their slow collision, something unprecedented was happening in what is now Siberia and India. Imagine the ground beginning to crack and split across thousands of square miles. Molten rock, superheated to over 2,000 degrees Fahrenheit, began forcing its way toward the surface through these massive fissures. This wasn't just a single volcanic eruption, but rather the largest volcanic event in Earth's recorded history. Lava flows stretched for hundreds of miles, creating rivers of molten rock that incinerated everything in their path. The immediate devastation was only the beginning. These volcanic eruptions pumped enormous quantities of toxic gases into the atmosphere. Carbon dioxide levels skyrocketed, creating a runaway greenhouse effect that pushed global temperatures up by at least 10 degrees Fahrenheit. But even more deadly were the massive amounts of sulfur compounds and methane released into the air. As temperatures rose, frozen methane deposits in the oceans began to melt and bubble to the surface, releasing even more greenhouse gases in a vicious cycle of warming. The oceans themselves became acidic and oxygen depleted. Marine ecosystems, which had taken millions of years to develop, collapsed almost overnight. On land, the situation was equally dire. Acid rain fell from poisonous skies, burning through the leaves of plants and contaminating water sources. The air became thick with volcanic ash and toxic particles, making it difficult for animals to breathe. Temperatures soared to levels that most life forms simply couldn't survive. Picture the once thriving Permian ecosystems reduced to barren wastelands. The mighty Dimetrodon, perfectly adapted to its environment, found itself unable to cope with the rapidly changing conditions. The elaborate food webs that had sustained diverse communities of predators and prey began to unravel as plant life died off and herbivores starved. Yet, in this global catastrophe, some creatures found ways to endure. The small burrowing cynodonts that had lived in the shadows of larger predators discovered that their underground lifestyle provided crucial protection from the toxic atmosphere and extreme temperatures. Their fur-covered bodies and efficient metabolisms allowed them to survive on limited food resources when larger animals perished. More importantly for our story, certain early archosaurs also managed to weather this crisis. These weren't impressive creatures by Permian standards, many no larger than modern lizards, but they possessed several key advantages that would prove crucial in the devastated world that emerged from the extinction. Their respiratory systems were more efficient than those of their contemporaries, allowing them to extract oxygen from air that had become depleted and contaminated. Their skin was scaly and water-resistant, protecting them from acid rain and helping them retain moisture in the increasingly arid post-extinction landscape. Perhaps most critically, their eggs had thick protective shells that could shield developing embryos from the harsh environmental conditions. The Great Dying, as scientists now call this extinction event, eliminated between 90 and 95% of all species on Earth. Entire groups of animals that had dominated for millions of years simply vanished forever. The mammal-like reptiles that had been so successful during the Permian were reduced to a handful of survivors. The diverse marine ecosystems were stripped bare, leaving behind a biological wasteland. But extinction events, as devastating as they are, also create opportunities. With so many ecological niches suddenly empty, the few survivors found themselves in a world with drastically reduced competition. The stage was set for one of the most remarkable evolutionary radiations in Earth's history. As the volcanic activity finally subsided and the immediate effects of the catastrophe began to fade, life slowly started to recover. But this wasn't a return to the Permian world. The survivors were different, and they would rebuild the biosphere according to new rules. The early Triassic period that followed was a time of experimentation and rapid evolution. The climate remained hot and largely arid, with much of Pangaea still covered by vast deserts. Seasonal rains would bring brief periods of abundance, but these were followed by long, harsh, dry seasons that tested every survival strategy. In this challenging environment, the ancestors of dinosaurs began their remarkable transformation. These early archosaurs were still small and generalized, but they were already showing signs of the innovations that would eventually make their descendants the rulers of the earth. One of their most significant advantages was their posture. Unlike the sprawling gait of most reptiles, these early dinosaur ancestors walked with their legs positioned directly beneath their bodies. This upright stance was far more energy efficient and allowed for faster, more sustained locomotion. When resources became scarce and migration became necessary for survival, this efficiency could mean the difference between life and death. Their breathing systems were also becoming increasingly sophisticated. While other reptiles had simple lungs, the archosaur lineage was developing air sacs, similar to those found in modern birds. This innovation allowed them to extract more oxygen from each breath, a crucial advantage in the oxygen-poor atmosphere of the early Triassic. Perhaps most importantly, many of these early forms were becoming warm-blooded, or at least partially warm-blooded. This meant they could remain active during cooler periods when their cold-blooded competitors were sluggish. In a world where food was often scarce and competition was intense, the ability to hunt or forage around the clock provided a significant edge. The first true dinosaurs appeared roughly 230 million years ago, emerging from this lineage of increasingly specialized archosaurs. These weren't the giants we typically envision when we think of dinosaurs. Most were no larger than a turkey, and many were considerably smaller. They were primarily bipedal, running on their hind legs with their arms free for grasping and manipulating objects. What made these early dinosaurs successful wasn't their size or their weapons, but their adaptability and efficiency. They could exploit food sources that other animals couldn't access. They could travel long distances when necessary, and they could remain active in conditions that would disable their competitors. The world they inhabited was still harsh and unpredictable. Massive crocodile-like predators, survivors from the Permian extinction, still dominated many ecosystems. These formidable hunters, some reaching lengths of over 25 feet, represented the old order of reptilian predators. They were powerful and well-armored, but they were also energy-intensive and required large amounts of food to maintain their massive bodies. The early dinosaurs, by contrast, were lean and efficient. They could survive on smaller prey and required less food to maintain their active lifestyles. When times were tough, they could outlast their larger competitors through sheer endurance. As the Triassic period progressed, these small dinosaurs began to diversify rapidly. Some remained small and agile, perfecting their roles as quick-moving predators of insects and small vertebrates. Others began to experiment with plant-eating lifestyles, developing the digestive adaptations necessary to process tough vegetation. The herbivorous dinosaurs faced unique challenges in the Triassic world. Plant life was still recovering from the extinction, and much of the available vegetation was tough and fibrous. These early plant eaters developed powerful jaw muscles and specialized teeth for grinding plant material. Some began to increase in size as larger bodies could house the longer digestive tracts needed to process plant matter efficiently. But the most significant development was yet to come. Toward the end of the Triassic period, another extinction event struck the Earth. This time, the disaster was smaller in scale than the Great Dying, but it was precisely targeted in its effects. Many of the large archosaur predators that had dominated Triassic ecosystems were wiped out, along with numerous other reptile groups. The dinosaurs, however, not only survived this second extinction, but emerged from it as the dominant land animals on Earth. The ecological niches left vacant by the extinction victims were quickly filled by rapidly evolving dinosaur species. This was the moment when dinosaurs truly began their rise to planetary dominance. The stage was now set for the golden age of dinosaurs. The Jurassic period was about to begin, and with it would come the emergence of the giants that capture our imagination today. But that transformation from small, scrappy survivors to colossal titans ruling land, sea, and sky is a story that deserves its own chapter in this epic tale. The Jurassic period dawned 201 million years ago, ushering in what would become the most iconic chapter in dinosaur history. But this wasn't an immediate transformation from small survivors to towering giants. The early Jurassic world was still recovering from the extinction that had ended the Triassic, and the dinosaurs that emerged were still finding their footing in a rapidly changing world. Gutstep, picture the Earth during this time, and you'd witness a planet in the midst of dramatic transformation. The supercontinent Pangaea was beginning to crack apart, with massive rifts opening up that would eventually become the Atlantic Ocean. These geological upheavals triggered intense volcanic activity, pumping carbon dioxide into the atmosphere and creating a greenhouse world far warmer than anything we know today. The climate was hot and humid across most of the planet, with no polar ice caps and sea levels much higher than today. Lush forests of conifers, ferns, and cycads covered the landscape, creating the perfect conditions for herbivorous dinosaurs to flourish. But there was something missing from these forests that we take for granted today. Flowers. The first flowering plants wouldn't appear until much later, so the Jurassic world was painted in shades of green and brown, without the colorful blooms that characterize modern ecosystems. In the warm, shallow seas that flooded much of the continental margins, marine reptiles were undergoing their own evolutionary explosion. Ichthyosaurs, the dolphin-like reptiles of the Mesozoic, reached their peak diversity during this period. Some species grew to enormous sizes, with the largest specimens stretching over 60 feet in length. These weren't lumbering giants, but rather sleek, powerful swimmers perfectly adapted for life in the open ocean. Their most remarkable feature was their eyes. Some ichthyosaurs had eyes over 2 feet in diameter, the largest of any known vertebrate. These massive visual organs allowed them to hunt in the deep, dark waters where sunlight barely penetrated, at depths where human eyes would see nothing but blackness. These marine predators could still track their prey with deadly precision. But the real stars of the Jurassic seas were the plesiosaurs, and they came in 2 dramatically different forms. The long-necked varieties, with necks containing up to 76 vertebrae, moved through the water like living periscopes. They weren't built for speed, but rather for stealth and patience. These creatures would hover motionless in the water, their enormous necks allowing them to position their heads precisely where schools of fish or swarms of marine invertebrates were most concentrated. Their hunting strategy was unlike anything we see in modern oceans. They would remain perfectly still, conserving energy, then suddenly strike with lightning speed when prey came within range. The neck, while appearing cumbersome, was actually a sophisticated hunting tool that allowed them to feed efficiently in the nutrient-rich Jurassic seas. The short-necked plesiosaurs, known as pliosaurs, were the apex predators of their time. These were the killer whales of the Mesozoic, built for power and speed rather than stealth. Some species reached lengths comparable to modern sperm whales, but they were far more aggressive and equipped with teeth that could crush almost any prey they encountered. Above the surface, the skies were beginning to host some of the most remarkable flying creatures ever to exist. Pterosaurs had survived the end-Triassic extinction and were rapidly diversifying into new forms. Early Jurassic pterosaurs were still relatively small, most with wingspans no greater than a few feet, but they were already showing signs of the incredible diversity that would characterize this group throughout the Mesozoic. These weren't primitive gliders, but sophisticated flying machines with complex wing membranes and advanced flight control systems. Some species developed elaborate crests on their heads, likely used for display and species recognition. Others evolved specialized feeding adaptations, with some becoming fish eaters, while others focused on insects or small terrestrial prey. But perhaps the most significant development in the Jurassic skies was the appearance of the first birds. Archaeopteryx, discovered in the limestone quarries of Germany, represents one of the most important transitional fossils ever found. These crow-sized creatures retained many reptilian features: teeth, clawed fingers, and long bony tails. But they also possessed true feathers and the ability to fly. The evolution of flight was one of the most remarkable achievements in the history of life, and the Jurassic period saw this innovation perfected by multiple groups independently. The competition between pterosaurs and early birds would drive both groups to remarkable heights of aerial sophistication. On land, dinosaurs were beginning their transformation into the giants that would define the later Mesozoic. The early Jurassic saw the emergence of the first truly large dinosaurs, though they were still modest compared to what was to come. Dilophosaurus, one of the most recognizable predators of this time, stretched about 23 feet in length and weighed nearly half a ton. This wasn't just a scaled-up version of earlier dinosaurs, but rather a fundamentally different kind of predator. Dilophosaurus had a relatively light build for its size, with long, powerful legs that could carry it at considerable speed across the Jurassic landscape. Its most distinctive features were the twin crests that adorned its skull, delicate bone structures that were almost certainly used for display rather than combat. These crests tell us something important about Jurassic dinosaur behavior. They suggest that these animals were engaging in complex social interactions, using visual displays to communicate with members of their own species. This wasn't just about finding mates, but likely involved territorial disputes, dominance hierarchies, and other sophisticated behaviors that we typically associate with more advanced animals. The herbivorous dinosaurs of the early Jurassic were also beginning to experiment with larger body sizes. Volcanodon, discovered in Zimbabwe, represents one of the earliest members of the sauropod lineage that would eventually produce the largest land animals in Earth's history. At about 20 feet in length and weighing several tons, Volcanodon was already showing the characteristic features that would define this group: a long neck, small head, and massive body, supported by column-like legs. But these early giants faced unique challenges. The vegetation of the Jurassic was very different from modern plant communities. There were no grasses, no fruits, and no flowers. Instead, herbivorous dinosaurs had to make do with tough conifers, fibrous ferns, and the palm-like leaves of cycads. Processing this low-quality food required significant adaptations in both behavior and anatomy. Many of these early herbivores developed gastroliths, stones that they deliberately swallowed to help grind up plant material in their stomachs. Paleontologists have found polished stones associated with dinosaur fossils from all over the world, evidence that these animals were actively managing their digestion in ways that no modern reptiles do. The success of herbivorous dinosaurs during the Jurassic created opportunities for new types of predators. As plant eaters grew larger and more numerous, carnivorous dinosaurs evolved to exploit this abundant food source. Megalosaurus, one of the first dinosaurs ever scientifically described, was a formidable predator perfectly adapted to hunting the herbivorous dinosaurs of its time. At about 30 feet in length and weighing over a ton, Megalosaurus was built like a precision killing machine. Its teeth were blade-like and serrated, designed to slice through flesh and bone with devastating efficiency. But perhaps more importantly, it was an intelligent hunter with a relatively large brain for its body size and sophisticated sensory systems. The arms of Megalosaurus were surprisingly small relative to its body size, a feature that would become even more pronounced in later predatory dinosaurs. This might seem like a disadvantage, but it actually reflects a fundamental shift in how these predators operated. Rather than grappling with their prey like earlier archosaurs, these dinosaurs were becoming specialized headhunters, using their massive skulls and powerful jaws as their primary weapons. This evolutionary trend toward larger, more specialized predators and prey created an arms race that would drive dinosaur evolution throughout the Mesozoic. Herbivores developed increasingly sophisticated defenses, armor, spikes, herding behaviors, and sheer size, while predators evolved ever more deadly hunting techniques. The Middle Jurassic saw this evolutionary arms race reach new heights. The climate became even warmer and more humid, supporting incredibly lush vegetation that could sustain ever larger herbivorous dinosaurs. The breakup of Pangaea was creating new habitats and isolating populations, allowing evolution to experiment with different solutions to the challenges of survival. It was during this time that the first true giant dinosaurs appeared. Cetiosaurus, reaching lengths of over 50 feet and weights approaching 25 tons, was a harbinger of the colossal sauropods that would dominate later periods. These weren't just large animals. They represented a completely new way of life that had never existed before on land. The logistics of being a giant herbivore required solutions to problems that no land animal had ever faced. How do you support a body weighing dozens of tons? How do you pump blood up a neck that might be 30 feet long? How do you find enough food to fuel such a massive metabolism? The answers that dinosaurs evolved to these questions were nothing short of revolutionary. Their bones became hollow like those of birds, reducing weight without sacrificing strength. Their hearts became massive, multi-chambered organs capable of generating the pressure needed to pump blood to their brains. Their digestive systems became incredibly efficient, capable of extracting maximum nutrition from low-quality plant material. But perhaps most remarkably, these giants developed complex social behaviors that allowed them to exploit their environment more effectively than any individual could alone. Evidence suggests that many sauropods lived in herds, with adults protecting juveniles and different age groups occupying different ecological niches within the same habitat. The late Jurassic marked the true golden age of dinosaur diversity. The continents were now well separated, creating isolated evolutionary laboratories where different groups of dinosaurs could pursue different evolutionary strategies. In North America, massive sauropods like Diplodocus and Brontosaurus dominated the landscape, their incredibly long necks allowing them to feed on vegetation that other herbivores couldn't reach. These weren't just scaled-up versions of earlier dinosaurs, but rather highly specialized feeding machines. Diplodocus, with its whip-like tail containing over 80 vertebrae, could have used this appendage as both a weapon and a communication device. The sound of a Diplodocus tail cracking like a whip might have been audible for miles, serving as a long-distance communication system in the vast Jurassic landscapes. Meanwhile, in what is now Portugal and other parts of Europe, different evolutionary experiments were taking place. Stegosaurus, with its distinctive rows of plates and spiked tail, represented a completely different approach to herbivorous defense. Rather than relying on size alone, these dinosaurs developed sophisticated armor systems that could deter even the largest predators. The plates of Stegosaurus have puzzled scientists for decades. Were they for defense, temperature regulation, or display? The answer is probably all three. These structures were filled with blood vessels that could flush with blood to create impressive visual displays, while also serving as solar panels to help regulate body temperature and providing some protection against predator attacks. The success of these armored herbivores created new opportunities for predators. Allosaurus, the apex predator of the late Jurassic, was perfectly adapted to hunt even the most heavily defended prey. At over 30 feet in length and weighing several tons, Allosaurus combined size, speed, and intelligence in a way that made it one of the most formidable predators ever to walk the earth. But Allosaurus wasn't just a mindless killing machine. Evidence suggests these predators were capable of complex behaviors, including cooperative hunting and possibly even rudimentary tool use. Some specimens show evidence of injuries that could only have been sustained while hunting dangerous prey, suggesting that these animals were willing to take significant risks to secure large meals. Sir, the late Jurassic also saw the emergence of some of the smallest dinosaurs ever discovered. Compsognathus, no larger than a chicken, represented the other end of the size spectrum from the giant sauropods. These tiny predators were incredibly agile and intelligent, capable of catching fast-moving prey like insects and small vertebrates that larger predators couldn't efficiently pursue. The coexistence of giants and miniatures in the same ecosystems demonstrates just how diverse and complex Jurassic dinosaur communities had become. Every ecological niche, from tiny insectivore to massive herbivore, was occupied by specialized dinosaur species, creating food webs of incredible complexity and stability. This diversity extended beyond land into the air and water as well. Pterosaurs were reaching new sizes and developing increasingly specialized feeding strategies. Some species evolved filter feeding mechanisms, similar to modern baleen whales, while others became aerial fishers with elaborate techniques for snatching prey from the water's surface. In the oceans, marine reptiles were reaching their own peaks of diversity and size. The largest marine predators of all time lived during the Jurassic, with some pliosaurs reaching lengths that rivaled modern blue whales. These weren't filter feeders, however, but active predators capable of taking down prey as large as other marine reptiles. The world of the late Jurassic was a planet dominated by reptiles in a way that has never been equaled before or since. From the tiniest pterosaur to the largest sauropod, from the deepest ocean to the highest mountain, reptilian life had conquered every available habitat and evolved solutions to every conceivable survival challenge. But this incredible diversity and success contained the seeds of vulnerability. The very specialization that made Jurassic dinosaurs so successful also made them dependent on stable environmental conditions. The complex food webs that supported dozens of species in each ecosystem required predictable resources and climate patterns. As the Jurassic period drew to a close, subtle changes were beginning to affect the global climate. Sea levels started to drop slightly, and temperature patterns began to shift. These changes were minor compared to the catastrophic extinctions that had marked earlier transitions, but they were enough to begin reshuffling the biological deck. The stage was being set for the final act in dinosaur evolution, the Cretaceous period, when these remarkable animals would reach their absolute peak of diversity, size, and ecological dominance, only to face their ultimate test in an extinction event that would end their What? A 60 million year reign forever. The transition from the Jurassic to the Cretaceous period, 145 million years ago, marked the beginning of dinosaur evolution's final and most spectacular chapter. This wasn't just another geological boundary. It was the gateway to an era that would see dinosaurs achieve their ultimate evolutionary triumph, while simultaneously setting the stage for their most devastating defeat. The world that emerged in the early Cretaceous was dramatically different from the Jurassic paradise that preceded it. Pangaea's breakup was accelerating, and the familiar supercontinent was fragmenting into recognizable continental shapes. North and South America were pulling away from Africa and Europe, while India began its epic journey northward toward its eventual collision with Asia. Australia and Antarctica were still joined, but even they were beginning their slow separation. These massive geological changes created entirely new climate patterns across the globe. The early Cretaceous was initially cooler than the late Jurassic, with ice caps forming at the poles for the first time in millions of years. Seasonal weather patterns became more pronounced, creating wet and dry seasons that would challenge dinosaur populations in unprecedented ways. But perhaps the most revolutionary change was botanical. During the early Cretaceous, flowering plants, angiosperms, made their first appearance on Earth. This might seem like a minor detail, but the evolution of flowers would transform every terrestrial ecosystem on the planet. These new plants didn't just add color to the landscape. They created entirely new ecological relationships that would drive the final phase of dinosaur evolution. Flowering plants were more nutritious than the conifers and ferns that had dominated earlier periods. They grew faster, reproduced more efficiently, and created new types of food resources: nectar, pollen, fruits, and nuts. This botanical revolution provided the energy foundation that would support the largest land animals in Earth's history. The early Cretaceous dinosaur world was still dominated by familiar groups from the Jurassic, but they were beginning to evolve in remarkable new directions. Sauropods, the long-necked giants, were reaching sizes that challenged the very limits of what land animals could achieve. Alamosaurus, one of the last and largest of these titans, stretched nearly 100 feet from nose to tail and weighed as much as 80 tons. Supporting such massive bodies required engineering solutions that pushed biological systems to their absolute limits. These giants developed pneumatic bone structures filled with air spaces, making their skeletons simultaneously lighter and stronger. Their hearts became four-chambered powerhouses, capable of pumping blood up necks that could reach 40 feet in length. Their digestive systems evolved into massive fermentation chambers that could extract every possible calorie from plant material. But the most remarkable adaptation was behavioral. Evidence suggests that the largest sauropods lived in complex social groups with sophisticated communication systems. They may have used infrasonic calls, sounds below the range of human hearing, to coordinate movements across vast distances. Imagine the haunting songs of these gentle giants echoing across Cretaceous landscapes, a form of communication that modern elephants still use today. The success of giant herbivores created opportunities for equally impressive predators. The early Cretaceous saw the emergence of some of the most formidable carnivorous dinosaurs ever to walk the earth. Acrocanthosaurus, a massive predator from what is now North America, reached lengths of over 40 feet and possessed a distinctive sail-like ridge along its back. This wasn't just for show. The ridge likely served as a thermoregulatory device and possibly as a display structure for intimidating rivals and attracting mates. These predators were far more sophisticated than their Jurassic predecessors. They possessed enhanced sensory systems, with some species developing keen senses of smell that could track prey across vast distances. Their brains were proportionally larger, suggesting increased intelligence and more complex hunting behaviors. Some may have hunted in coordinated groups, using tactics that wouldn't look out of place in a nature documentary about modern wolves or lions. But the most significant development in early Cretaceous predator evolution was the emergence of the Tyrannosaur lineage. The early members of this group were still relatively modest in size, but they already possessed the key innovations that would make their descendants the most feared predators in Earth's history. Powerful jaw muscles, bone-crushing teeth, and enhanced sensory systems were already present in these early forms. The plant-eating dinosaurs of the early Cretaceous were also undergoing remarkable evolutionary experiments. The arrival of flowering plants created new dietary opportunities, but it also created new challenges. Many of these plants contained toxic compounds designed to deter herbivores, leading to an evolutionary arms race between plants and their consumers. Iguanodon, one of the most successful herbivores of this period, developed sophisticated dental batteries, rows of grinding teeth that could process the toughest plant material. These weren't just simple chewing mechanisms, but rather complex food processing systems that could handle everything from soft leaves to woody stems. The animals also developed powerful thumb spikes that served both as weapons and as tools for manipulating vegetation. The diversity of herbivorous dinosaurs during the early Cretaceous was staggering. Massive titanosaurs roamed South America and Africa, their bodies protected by bony armor plates embedded in their skin. Duck-billed hadrosaurs began their evolutionary radiation in Asia, developing hollow crests that functioned as sophisticated sound-producing organs. Armored ankylosaurs perfected their defensive strategies, becoming living tanks that few predators dared to attack. This period also witnessed one of the most remarkable evolutionary innovations in dinosaur history, the development of true social behavior. Evidence from fossil bone beds suggests that many species lived in large herds with complex social structures. Young animals were protected by adults. Different age groups occupied different positions within the herd, and sophisticated communication systems allowed these groups to coordinate their movements across vast distances. The skies above the early Cretaceous world were becoming increasingly crowded with flying reptiles. Pterosaurs were reaching their peak diversity, with some species evolving to fill ecological niches that no flying animal has occupied since. Quetzalcoatlus, though it wouldn't appear until later in the Cretaceous, represents the ultimate expression of pterosaur evolution, a flying reptile with a wingspan approaching 35 feet that could soar over vast distances while hunting on both land and water. These weren't just scaled-up versions of earlier pterosaurs, but rather highly specialized flying machines with adaptations that seem almost alien to modern eyes. Some species developed elaborate crests that may have functioned as both display structures and flight control surfaces. Others evolved filter-feeding mechanisms that allowed them to strain small organisms from water like living aerial baleen whales. The competition between pterosaurs and the rapidly evolving birds was becoming increasingly intense. Birds were developing more sophisticated flight capabilities and beginning to occupy ecological niches that had previously been dominated by pterosaurs. This competition would drive both groups to remarkable heights of aerial specialization. In the oceans, marine reptiles were facing their own evolutionary pressures. The ichthyosaurs that had dominated Jurassic seas were beginning to decline, unable to compete with new groups of marine predators. Mosasaurs, massive marine lizards, were emerging as the new rulers of the sea. These weren't just large lizards that had taken to water, but rather highly specialized marine predators with adaptations that rivaled those of modern whales and dolphins. The largest mosasaurs reached lengths of over 50 feet and possessed jaw muscles capable of crushing the shells of the largest ammonites. They developed paddle-like limbs, streamlined bodies, and sophisticated sensory systems that allowed them to hunt effectively in the murky waters of Cretaceous seas. Some species may have been warm-blooded, giving them the metabolic advantages needed to compete with other marine predators. But perhaps the most significant development in early Cretaceous marine ecosystems was the evolution of new types of sharks. Modern shark families were beginning to emerge, bringing with them innovations in tooth design, body structure, and hunting behavior that would prove incredibly successful. These new sharks would not only survive the coming extinction, but would continue to dominate marine ecosystems for the next 100 million years. As the early Cretaceous progressed into the late Cretaceous, the pace of evolutionary change accelerated dramatically. The continued breakup of the continents was creating isolated populations that could evolve independently, leading to an explosion of diversity that would make the late Cretaceous the most dinosaur-rich period in Earth's history. The climate was warming again, returning to the greenhouse conditions that had characterized much of the Mesozoic. Sea levels rose to their highest points ever recorded, flooding vast areas of the continents and creating warm, shallow seas that supported incredibly productive ecosystems. These inland seas became nurseries for marine reptiles and fish, while their shores supported diverse communities of dinosaurs and other terrestrial animals. The late Cretaceous world was a planet at the absolute peak of biological diversity and productivity. Flowering plants had revolutionized terrestrial ecosystems, creating complex forest communities that supported more species than had ever existed before. Dinosaurs had evolved to fill every conceivable ecological niche, from tiny feathered insectivores to colossal herbivores that dwarfed modern elephants. This was the world that would produce Tyrannosaurus rex, the ultimate expression of predatory evolution. Standing 20 feet tall and weighing up to 9 tons, T-Rex wasn't just large. It was a perfect killing machine, equipped with sensory systems that could detect prey from miles away, bone-crushing jaws that could exert more pressure per square inch than any land animal before or since, and a brain sophisticated enough to coordinate complex hunting strategies. But T-Rex was just one member of an incredibly diverse community of late Cretaceous predators. Smaller raptors like Velociraptor hunted in coordinated packs using sickle-shaped claws and sophisticated communication to bring down prey much larger than themselves. Massive crocodilians like Dinosaurs lurked in rivers and swamps, capable of taking down even the largest dinosaurs that came to drink. The herbivorous dinosaurs of the late Cretaceous were equally impressive. Triceratops, with its massive three-horned skull and bony frill, wasn't just defending itself from predators. It was engaging in complex social behaviors that included ritualized combat between rivals and elaborate courtship displays. These animals lived in herds that may have numbered in the thousands, creating some of the most spectacular wildlife spectacles in Earth's history. Hadrosaurs had evolved into incredibly diverse forms, with different species developing unique crest shapes that functioned as species-specific sound-producing organs. The calls of these animals would have created a symphony of sounds across late Cretaceous landscapes, a form of acoustic communication that rivaled anything found in modern ecosystems. The armored dinosaurs reached their ultimate expression in forms like Ankylosaurus, living fortresses covered in bony plates and armed with massive tail clubs that could shatter the bones of any predator foolish enough to attack. These weren't passive defenders, but rather active participants in the complex ecological relationships that characterize late Cretaceous communities. In the air, pterosaurs had evolved into forms that challenge our understanding of what flying animals can achieve. The largest species had wingspans that exceeded those of small aircraft, yet they were capable of powered flight and sophisticated aerial maneuvers. They occupied ecological niches, from tiny insectivores to massive aerial predators that could soar over continents. Birds were also reaching new heights of diversity and sophistication. While still retaining many primitive features, they were developing the flight capabilities and ecological adaptations that would allow them to survive the coming catastrophe and inherit the post-dinosaur world. The late Cretaceous represented the absolute pinnacle of reptilian evolution. Never before or since has any single group of animals achieved such complete dominance over terrestrial ecosystems. Dinosaurs had conquered every habitat, evolved solutions to every survival challenge, and created ecological communities of unprecedented complexity and stability. But this very success contained the seeds of vulnerability that would prove fatal when disaster struck. The highly specialized nature of late Cretaceous ecosystems meant that they were dependent on stable environmental conditions. The complex food webs that supported dozens of species required predictable resources and climate patterns. The giant size that many dinosaurs had achieved made them vulnerable to rapid environmental changes. As the late Cretaceous drew to a close, subtle signs were beginning to suggest that changes were coming. Volcanic activity was increasing in some parts of the world, and climate patterns were showing signs of instability. But nothing in the preceding 160 million years of dinosaur evolution had prepared these magnificent creatures for what was about to unfold. The stage was set for one of the most dramatic and sudden reversals of fortune in the history of life on Earth. In a matter of hours, the most successful animals that had ever lived would face their ultimate test, and most would fail. The age of dinosaurs was about to end not with a gradual decline, but with a catastrophe so sudden and complete that it would reshape the entire history of life on our planet. The final act of the dinosaur sagas was about to begin with an event so catastrophic, so sudden, that it would make the previous mass extinctions look like minor hiccups in Earth's history. 66 million years ago, as the late Cretaceous world basked in its unprecedented diversity and abundance, something was hurtling through the darkness of space toward our planet. A mountain-sized asteroid traveling at speeds that defy comprehension. But before we witness this cosmic collision, let's step into the world that was about to be destroyed forever. Imagine walking through the forests of what would one day become North America. The air is thick and humid, filled with the calls of countless creatures that have no modern equivalent. Towering overhead are massive conifers and the newly evolved flowering trees, their canopies alive with pterosaurs whose wingspans rival those of small aircraft. The ground trembles beneath your feet as a herd of triceratops moves through the forest, their massive three-horned skulls pushing through the undergrowth like living bulldozers. These aren't solitary animals, but social creatures living in complex herds with sophisticated communication systems. The bony frills adorning their heads aren't just armor. They're billboards advertising their health, status, and readiness to mate. Behind them, keeping a respectful distance, stalks one of the most perfect predators ever evolved. Tyrannosaurus rex moves with surprising grace for an animal weighing as much as a city bus. Its massive skull houses a brain more sophisticated than any reptile before or since, capable of processing sensory information with the precision of a guided missile. Those bone-crushing jaws aren't just weapons. They're precision instruments capable of delivering over 12,000 pounds of pressure per square inch. But T-Rex isn't alone in its domain. The late Cretaceous world supported an incredible diversity of predators, each perfectly adapted to their specific hunting strategies. Velociraptors hunt in coordinated packs, their sickle-shaped claws and keen intelligence making them formidable opponents for prey many times their size. These aren't the oversized monsters of Hollywood movies, but rather turkey-sized hunters whose real weapon was their brain, not their brawn. In the rivers and coastal areas, massive crocodilians like Dinosaurs patrol the waters. These aren't the crocodiles we know today, but giants reaching lengths of over 40 feet, capable of taking down even the largest dinosaurs that venture too close to the water's edge. Their powerful jaws and armored bodies make them virtually invincible in their aquatic domain. The herbivorous dinosaurs of this time represent the pinnacle of plant-eating evolution. Hadrosaurs, the duck-billed dinosaurs, have developed incredible diversity in their head crests, each species creating unique sounds that echo across the landscape like prehistoric orchestras. Some species produce deep, resonant calls that can be heard for miles, while others create higher-pitched tones that serve as intimate communication between family members. These aren't simple feeding machines, but sophisticated animals with complex social behaviors. Fossil evidence suggests they lived in herds that could number in the thousands, with different age groups occupying specific positions within the group for optimal protection and resource access. Young animals were shielded in the center of the herd, while experienced adults took positions on the periphery, where they could watch for danger. The armored dinosaurs had reached their ultimate expression in creatures like Ankylosaurus, living tanks covered in bony plates and armed with massive tail clubs that could shatter the leg bones of even the largest predators. These defensive adaptations weren't passive. Evidence suggests these animals could actively wield their tail weapons with devastating accuracy, turning their entire bodies into formidable defensive systems. But perhaps the most awe-inspiring dinosaurs of the late Cretaceous were the sauropods that still roamed certain parts of the world. Alamosaurus, one of the last giants, stretched nearly 100 feet in length and weighed as much as a dozen elephants. These weren't just large animals. They were biological marvels that pushed the very limits of what land-dwelling creatures could achieve. Supporting such massive bodies required innovations that seem almost alien to modern biology. Their bones were filled with air spaces like those of birds, creating structures that were simultaneously lighter and stronger than solid bone. Their hearts were massive organs capable of pumping blood up necks that could reach 40 feet in height. Their digestive systems were living fermentation chambers that could extract every possible calorie from plant material. The skies above this incredible world were dominated by pterosaurs that had evolved to sizes and specializations that challenge our understanding of flight. Quetzalcoatlus, with its 35-foot wingspan, wasn't just a flying animal. It was an aerial giant capable of soaring for hundreds of miles while hunting on both land and water. These creatures possessed hollow bones, sophisticated flight muscles, and navigation systems that allowed them to exploit atmospheric currents with incredible efficiency. Sharing the skies were increasingly diverse birds, still retaining many primitive features, but beginning to develop the characteristics that would allow them to inherit the post-dinosaur world. The competition between birds and pterosaurs was driving both groups to remarkable heights of aerial sophistication. In the warm, shallow seas that covered much of the continental interiors, marine reptiles had reached their own peaks of evolutionary success. Mosasaurs, massive marine lizards, ruled the oceans with the authority of modern great white sharks. The largest species reached lengths of over 50 feet and possessed adaptations that rivaled those of whales. Streamlined bodies, powerful swimming muscles, and sophisticated sensory systems for hunting in murky water. These marine giants shared their domain with equally impressive plesiosaurs, some with necks so long they could reach their heads around their own bodies. The largest marine predators of all time lived during this period, creating ocean ecosystems of incredible complexity and productivity. But beneath this veneer of success and abundance, subtle changes were beginning to affect the global environment. Volcanic activity was increasing in what is now India, creating massive lava flows that would eventually cover an area larger than modern France. These eruptions were pumping enormous quantities of gases into the atmosphere, gradually altering climate patterns across the globe. Sea levels were beginning to fluctuate, and temperature patterns were showing signs of instability. Some dinosaur populations were already showing signs of stress, with certain species declining in numbers or disappearing from their traditional ranges. But these changes were gradual and localized, nothing that suggested the coming catastrophe. The diversity of late Cretaceous life extended far beyond the dinosaurs themselves. Mammals, still small but increasingly diverse, were beginning to explore ecological niches that would prove crucial for their post-extinction success. Early primates were appearing in the fossil record along with the ancestors of modern carnivores, ungulates, and other major mammalian groups. Flowering plants had revolutionized terrestrial ecosystems, creating complex forest communities that supported more species than had ever existed before. The coevolution between plants and their pollinators had created intricate ecological relationships that made these ecosystems incredibly productive, but also highly interdependent. Insects had diversified into forms that included most of the major groups we recognize today. Ants had evolved complex social systems. Butterflies and moths were co-evolving with flowering plants. And beetles had become one of the most successful groups of organisms on the planet. The pollination relationships between insects and plants were creating the foundation for the modern terrestrial biosphere. This was a world at the absolute peak of biological complexity and productivity. Food webs included dozens of species at each trophic level, creating networks of interdependence that had taken millions of years to develop. Energy flowed through these systems with incredible efficiency, supporting biomasses that wouldn't be equaled again until the rise of modern mammalian megafauna. The climate of the late Cretaceous was remarkably stable and warm. There were no polar ice caps, and temperatures were relatively uniform across the globe. Seasonal variations were mild, and weather patterns were predictable. This climatic stability had allowed ecosystems to develop incredible complexity and specialization. But this very stability was about to become a vulnerability. The highly specialized nature of late Cretaceous ecosystems meant they were adapted to very specific environmental conditions. The giant size that many animals had achieved made them dependent on abundant food resources and stable habitats. The complex interdependencies between species meant that the loss of key groups could trigger cascading extinctions throughout entire ecosystems. As we stand on the brink of the most dramatic moment in the history of life on Earth, it's worth reflecting on what was about to be lost. The late Cretaceous represented the culmination of 160 million years of dinosaur evolution. These weren't primitive lumbering reptiles, but sophisticated animals with complex behaviors, advanced physiologies, and ecological relationships that rivaled anything in the modern world. Many of these creatures possessed intelligence levels that we're only beginning to appreciate. Evidence suggests that some dinosaurs engaged in play behavior, complex social rituals, and even rudimentary tool use. Their communication systems included not just vocalizations, but visual displays, chemical signals, and possibly even infrasonic calls that could travel for miles. The largest dinosaurs were engineering marvels that pushed biological systems to their absolute limits. The smallest were precision instruments of predation and survival. Between these extremes was a spectrum of forms and functions that filled every conceivable ecological niche on land, in the air, and in the water. But perhaps most remarkably, these animals had created stable ecosystems that persisted for millions of years. Unlike modern ecosystems, which are often disrupted by climate changes, volcanic eruptions, or other natural disasters, dinosaur-dominated communities showed remarkable resilience and longevity. Some ecosystem types persisted virtually unchanged for tens of millions of years. This stability wasn't the result of evolutionary stagnation, but rather the achievement of a kind of ecological perfection. Predator-prey relationships were finely balanced, resource utilization was incredibly efficient, and waste products from one species became resources for others. The dinosaur world had achieved something that modern ecosystems are still striving for: true sustainability. The asteroid that would end this incredible chapter in Earth's history was already on its final approach. Somewhere in the outer solar system, this mountain-sized chunk of rock and metal had been knocked from its stable orbit, perhaps by the gravitational influence of Jupiter or a collision with another asteroid. For millions of years, it had been falling toward the inner solar system, its trajectory gradually bending toward an appointment with Earth. As it passed through the asteroid belt, it may have collided with smaller objects, altering its composition and adding to its mass. By the time it entered Earth's gravitational field, it was a cosmic projectile weighing trillions of tons and traveling at speeds of over 40,000 miles per hour. The dinosaurs living their final day had no way of knowing what was coming. They went about their daily routines of hunting, feeding, caring for their young, and defending their territories, just as their ancestors had done for millions of generations before them. The great herds of Triceratops continued their migrations. The mighty Tyrannosaurus continued their hunts, and the gentle giants continued their endless search for vegetation. In just a few hours, an event lasting only seconds would bring this entire world crashing down. The impact would release energy equivalent to billions of nuclear weapons, triggering a cascade of catastrophes that would make the previous mass extinctions look insignificant by comparison. Shock waves would circle the globe multiple times. Mega tsunamis would scour the continents, and debris ejected into space would rain back down as molten rock, setting the entire planet on fire. But the immediate destruction would be only the beginning. The long-term consequences of the impact would prove even more devastating than the initial catastrophe itself. As we prepare to witness this ultimate test of survival, remember that what we're about to see isn't just the end of the dinosaurs. It's one of the most important moments in the history of life on Earth, setting the stage for the rise of mammals and ultimately our own existence. The final day of the age of dinosaurs was about to dawn, and with it, would come changes so profound that they would reshape the entire future of life on our planet. The morning of that final day dawned like countless others before it across the late Cretaceous world. In the coastal plains of what would one day become the Gulf of Mexico, a massive herd of Alamosaurus moved slowly through the dawn mist, their enormous necks sweeping through the canopy like living cranes. These gentle giants, some weighing nearly 80 tons, had no concept that they were living through the last sunrise their kind would ever see. Hundreds of miles to the north, in the river deltas and floodplains that stretched across the continent's interior, communities of hadrosaurs were beginning their daily routines. The haunting calls of Parasaurolophus echoed across the landscape as adults communicated the locations of fresh feeding grounds to their scattered family groups. Their hollow crests functioned like prehistoric trumpets, each species producing its own distinctive musical signature that could carry for miles through the humid air. The predators were stirring as well. A massive Tyrannosaurus rex, perhaps the most formidable land predator that had ever lived, was tracking the scent trail of a wounded Triceratops through a grove of primitive flowering trees. This particular T-Rex was a veteran hunter, bearing scars from countless battles and possessing the kind of predatory intelligence that had made its species the apex predators of their world. Its quarry, a 3-ton Triceratops with a skull nearly 8 feet long, was desperately seeking the safety of its herd. The distinctive 3-horned face that gave these animals their name wasn't just for show. Those horns were weapons capable of inflicting mortal wounds on even the largest predators. But injury had made this individual vulnerable, and the T-Rex's keen sense of smell had detected weakness from miles away. In the shallow inland seas that bisected the continent, a different kind of drama was unfolding. Massive mosasaurs, marine lizards that had grown to whale-like proportions, were engaged in their own hunts beneath the warm waters. These weren't the clumsy marine reptiles of earlier eras, but sophisticated predators with streamlined bodies and powerful swimming abilities that allowed them to pursue prey with remarkable efficiency. Above the surface, pterosaurs with wingspans exceeding 30 feet soared on thermals rising from the sun-warmed waters. These aerial giants, among the largest flying creatures ever to exist, were marvels of biological engineering. Their hollow bones and sophisticated flight membranes allowed them to stay aloft for hours while scanning the waters below for fish or the shorelines for carrion. The skies were increasingly shared with true birds, descendants of earlier dinosaurs that had taken to the air millions of years previously. While still retaining many primitive features like teeth and clawed wings, these early birds were developing the flight capabilities and metabolic advantages that would soon prove crucial for survival. In the dense forests that covered much of the continental interiors, smaller dinosaurs were going about their own business of survival. Packs of velociraptor-sized dromaeosaurs moved through the underbrush with the coordinated precision of modern wolves, their sickle-shaped claws and keen intelligence making them formidable hunters despite their relatively modest size. These weren't the oversized monsters of popular imagination, but rather precisely built killing machines about the size of large turkeys. Their real weapons weren't just their famous claws, but their sophisticated pack hunting strategies and their ability to communicate complex tactical information to their packmates through a combination of vocalizations, body language, and possibly even primitive gestures. Sharing the forest floor were the heavily armored ankylosaurs, living tanks that had perfected the art of passive defense. Their bodies were covered in bony plates and spikes, and their tails ended in massive clubs that could swing with bone-shattering force. These weren't helpless victims, but active participants in the complex predator-prey relationships that characterize late Cretaceous ecosystems. The plant life supporting all of this animal diversity was itself a marvel of evolution. Flowering plants had revolutionized terrestrial ecosystems, creating forests of incredible complexity and productivity. Oak-like trees, primitive magnolias, and early palms created multi-layered canopies that supported hundreds of species of insects, small vertebrates, and climbing plants. The co-evolutionary relationships between plants and their pollinators had created intricate networks of interdependence. Early bees, butterflies, and beetles had evolved alongside the flowering plants, creating pollination systems of remarkable efficiency. The fruits and seeds produced by these plants provided food resources that supported entire communities of animals, from tiny mammals to massive herbivorous dinosaurs. But beneath this veneer of abundance and stability, the planet was already experiencing subtle stresses that hinted at the vulnerability of these complex ecosystems. Massive volcanic eruptions in what is now India had been ongoing for thousands of years, pumping enormous quantities of carbon dioxide and sulfur compounds into the atmosphere. These eruptions, known today as the Deccan Traps, were creating the largest lava flows in Earth's history. The volcanic activity was gradually altering global climate patterns, causing temperature fluctuations and changing precipitation patterns across different regions. Some dinosaur populations were already showing signs of stress, with certain species declining in numbers or shifting their ranges in response to changing environmental conditions. Sea levels were also fluctuating, causing the vast inland seas that had characterized much of the Cretaceous to begin their slow retreat. This process was altering coastal ecosystems and changing the distribution of marine and terrestrial habitats. The highly specialized communities that had evolved in these transitional zones were particularly vulnerable to such changes. But these gradual environmental shifts, significant as they were, paled in comparison to what was hurtling toward Earth from the depths of space. The asteroid that would end the age of dinosaurs was now only hours away from impact, traveling at speeds that would carry it from the moon to Earth in less than 10 hours. This cosmic projectile, roughly 6 miles in diameter and weighing trillions of tons, was composed primarily of rock and metal, with traces of rare elements that would later serve as evidence of its extraterrestrial origin. As it approached Earth's atmosphere, it was moving at approximately 45,000 miles per hour, fast enough to circle the Earth in just over half an hour. The dinosaurs living through these final hours had no way of detecting the approaching catastrophe. Their sensory systems, remarkable as they were, had evolved to detect earthbound threats and opportunities. The concept of danger from space was entirely outside their evolutionary experience. In the Yucatan Peninsula, where the asteroid would soon create one of the largest impact craters in Earth's history, herds of hadrosaurs were feeding in coastal marshlands rich with aquatic vegetation. These duck-billed dinosaurs had evolved sophisticated dental batteries, rows of grinding teeth that could process even the toughest plant materials. Their feeding activities were creating the distinctive fossil deposits that paleontologists would discover millions of years later. Nearby, a group of small theropod dinosaurs were engaged in behaviors that would have seemed remarkably bird-like to modern observers. They were using tools, sticks, and stones to extract insects from tree bark and to crack open tough nuts and seeds. This kind of behavioral sophistication was becoming increasingly common among the smaller dinosaurs, suggesting cognitive abilities that rivaled those of modern intelligent birds. The social behaviors of late Cretaceous dinosaurs were reaching levels of complexity that we're only beginning to understand. Evidence suggests that many species engaged in elaborate courtship rituals, with males performing displays that involved intricate dances, colorful plumage, and complex vocalizations. Some species may have even engaged in gift-giving behaviors, offering food or nesting materials to potential mates. Parental care among dinosaurs had evolved to remarkable levels of sophistication. Many species built elaborate nests, regulated the temperature of their eggs through careful positioning and covering with vegetation, and provided extended care for their young after hatching. Some fossil sites preserve evidence of multi-generational family groups, suggesting that dinosaur social structures were far more complex than previously imagined. The communication systems used by these animals were equally impressive. Beyond the well-known vocalizations produced by hollow crests and specialized throat structures, many dinosaurs used visual displays involving colorful skin patterns, elaborate plumage, and coordinated body movements. Some species may have even used infrasonic calls, sounds below the range of human hearing, to communicate across vast distances. These communication abilities were particularly important for the massive sauropods, whose herds could stretch for miles across the landscape. Coordinating the movements of such enormous groups required sophisticated signaling systems that could convey information about food sources, water locations, and potential dangers across great distances. The predatory dinosaurs had developed hunting strategies that rivaled those of any modern predators. Large theropods like Tyrannosaurus rex weren't just mindless killing machines, but sophisticated hunters capable of planning complex attacks, working cooperatively with others of their species, and even using rudimentary tools in their hunts. Evidence suggests that some predatory dinosaurs engaged in ambush hunting, using their understanding of prey behavior to position themselves at strategic locations where their quarry was most vulnerable. Others may have used persistence hunting, following prey over long distances until exhaustion made them easy targets. The smaller predatory dinosaurs had developed pack hunting techniques that allowed them to take down prey many times their own size. These coordinated attacks required complex communication and planning abilities that indicate high levels of intelligence and social cooperation. As the final hours of the Cretaceous ticked away, these remarkable creatures continued their ancient patterns of behavior, unaware that they were living through the end of an era. The asteroid was now close enough that its gravitational influence was beginning to affect Earth's atmosphere, but these effects were far too subtle for any living creature to detect. The impact site in the Yucatan Peninsula was still just another stretch of shallow tropical sea, teeming with marine life and bordered by lush coastal forests. Massive marine reptiles cruised through waters that would soon be vaporized by temperatures exceeding those found in the core of the sun. Pterosaurs soared overhead on wings that would be torn apart by shock waves traveling faster than sound. In just a few hours, this entire world would be transformed beyond recognition. The impact would release energy equivalent to over 1 billion nuclear weapons, creating temperatures, pressures, and destructive forces unlike anything in the previous 4.5 billion years of Earth's history. But the story of that impact and its immediate aftermath, the minutes and hours that would reshape the planet and end the age of dinosaurs forever, represents the climactic moment of our journey through deep time. As we prepare to witness the most dramatic transformation in the history of life on Earth, we stand at the threshold between two worlds, the ancient realm of reptilian giants that had endured for 160 million years, and the new age of mammals that would rise from their ashes. The final act of the dinosaur saga was about to begin, and with it would come changes so profound and far-reaching that they would determine the entire future course of evolution on our planet. In just moments, cosmic and terrestrial forces would collide in an event that would make every previous mass extinction look like a minor disturbance in the long history of life. The countdown to catastrophe had begun, though no living creature on Earth could comprehend what was approaching. Somewhere high above the atmosphere, beyond the realm of pterosaurs and early birds, a mountain of rock and metal was making its final descent toward our planet. This cosmic bullet, forged in the depths of space billions of years ago, was about to collide with Earth at a velocity that would make the fastest dinosaur look motionless by comparison. But in these last precious hours before impact, life on Earth continued with the rhythm that had sustained it for millions of years. The great cycles of predator and prey, birth and death, competition and cooperation played out across every continent, just as they had countless times before. None of the magnificent creatures going about their daily business could imagine that they were participants in the final act of the greatest evolutionary success story in Earth's history. In the dense forests of what would one day become North Dakota, a different kind of drama was unfolding. Here, in an environment that resembled a cross between modern Louisiana bayous and Indonesian rainforests, some of the most advanced dinosaurs ever to exist were demonstrating behaviors that would have amazed any modern biologist lucky enough to witness them. A family group of triceratops had gathered around a natural salt lick, their massive three-horned skulls lowered as they consumed the mineral-rich deposits essential for their health. These weren't solitary animals, as often depicted in popular media, but highly social creatures with complex family structures that could span multiple generations. The largest individuals, their bony frills scarred from countless battles, stood guard while younger members of the group fed. The social dynamics playing out among these giants were remarkably sophisticated. Older, more experienced individuals had earned their positions through a combination of size, intelligence, and social savvy. They communicated through a combination of deep, rumbling calls, visual displays involving the positioning of their elaborate frills, and subtle body language that conveyed information about everything from food quality to potential threats. Watching from the shadows of the forest canopy was a pack of Dakota raptor, some of the largest and most formidable of the dromaeosaurid dinosaurs. These weren't the chicken-sized creatures that many people imagine when they think of raptor dinosaurs, but rather animals the size of large bears, equipped with sickle-shaped claws over 9 inches long and intelligence that rivaled that of modern dolphins. The pack had been stalking this Triceratops group for days, waiting for the right moment to strike. Their hunting strategy was a masterpiece of coordination and patience. Different pack members had specific roles: scouts who monitored the herd's movements, strategists who identified the most vulnerable targets, and attackers who would deliver the killing blows when the moment was right. But hunting Triceratops was among the most dangerous activities any predator could attempt. Those 3 horns weren't just for show. They were precision weapons capable of piercing even the thickest hide. The bony frill that adorned each animal's head could deflect attacks and protect vital areas of the neck and shoulders. Most importantly, these herbivores fought back with a ferocity that could turn hunters into prey in a matter of seconds. The lead Dakota raptor, a scarred veteran of many hunts, made a series of subtle gestures to its packmates. This wasn't random animal behavior, but rather a sophisticated form of communication that allowed the pack to coordinate complex tactical maneuvers. Each gesture conveyed specific information about timing, positioning, and individual responsibilities in the upcoming attack. Meanwhile, high above the forest canopy, one of the most remarkable creatures in Earth's history was soaring on thermals rising from the sun-warmed landscape below. Quetzalcoatlus, with a wingspan that exceeded that of a small aircraft, was a marvel of biological engineering that pushed the very limits of what flying animals could achieve. This wasn't just a scaled-up version of smaller pterosaurs, but rather a highly specialized aerial predator, with adaptations that seem almost alien to modern eyes. Its hollow bones were lighter than those of birds, yet strong enough to support its massive frame during flight. Its wing membranes were living structures filled with blood vessels and nerve endings that allowed for precise flight control in even the most challenging atmospheric conditions. The hunting strategy employed by Quetzalcoatlus was unlike anything practiced by modern flying animals. It could soar for hours without flapping its wings, using its keen eyesight to scan vast areas of landscape for potential prey. When it spotted a target, it could dive from tremendous heights, using gravity to accelerate to speeds that would make it virtually invisible to ground-dwelling animals until the moment of impact. But perhaps most remarkably, evidence suggests that some of these giant pterosaurs may have been capable of powered flight even after landing. Their wing structure and muscle attachments indicate that they could launch themselves back into the air from a standing position, giving them a versatility that no modern flying animal possesses. The world that these creatures inhabited was one of incredible abundance and diversity. The forests were multi-layered ecosystems that supported hundreds of species at different levels of the canopy. Flowering plants had created ecological relationships of stunning complexity with different species of insects, small mammals, and birds occupying highly specialized niches. At ground level, the forest floor was a bustling community of decomposers, scavengers, and small predators. Early mammals, still modest in size but increasingly diverse in their adaptations, were beginning to explore ecological opportunities that would prove crucial for their survival in the coming catastrophe. Some had developed enhanced hearing that allowed them to hunt insects in complete darkness. Others had evolved specialized climbing abilities that let them exploit resources in the forest canopy. These small mammals possessed several advantages that their dinosaur contemporaries lacked. Their fur provided excellent insulation, allowing them to maintain body temperature in conditions that would disable cold-blooded reptiles. Their relatively small size meant they required less food to survive, making them less vulnerable to disruptions in food webs. Most importantly, many species had developed the ability to enter torpor or hibernation-like states during times of environmental stress. But the mammals of the late Cretaceous were still living in the shadow of the dinosaurs, both literally and figuratively. The largest mammalian predators were no bigger than modern house cats, while the herbivorous species rarely exceeded the size of small dogs. They occupied ecological niches that the dominant reptiles either couldn't access or weren't interested in exploiting. The success of dinosaurs had created a world where reptilian solutions to survival challenges had been perfected over millions of years of evolution. The largest herbivores had developed digestive systems that could extract maximum nutrition from the toughest plant materials. The most formidable predators had evolved sensory systems that could detect prey from incredible distances and weapons that could dispatch even the most heavily defended victims. This specialization and efficiency had created ecosystems of remarkable stability and productivity. Energy flowed through these biological communities with minimal waste, supporting biomasses that wouldn't be equaled again until the rise of modern mammalian megafauna millions of years later. The marine ecosystems of the late Cretaceous were equally impressive in their diversity and complexity. The warm, shallow seas that covered much of the continental interiors supported communities of marine reptiles that had no modern equivalents. Mosasaurs ruled these waters with the authority of modern great white sharks. But their hunting strategies were far more sophisticated than anything practiced by contemporary marine predators. The largest mosasaurs had evolved echolocation abilities similar to those of modern dolphins, allowing them to hunt effectively in murky water or during nighttime hours. Their streamlined bodies and powerful swimming muscles enabled them to pursue prey at speeds that would have been impossible for earlier marine reptiles. Some species had even developed the ability to leap partially out of the water when attacking surface prey, much like modern killer whales. Sharing these waters were the last of the great plesiosaurs, marine reptiles with necks so long and flexible that they could literally tie themselves in knots. These weren't just passive filter feeders, but active predators capable of complex hunting behaviors. Some species may have used their incredibly long necks as lures, positioning their small heads to mimic smaller prey animals while their massive bodies remained hidden in deeper water. The ammonites that shared these seas with the marine reptiles had reached their own peaks of evolutionary sophistication. These cephalopods, related to modern squid and octopus, had developed shells of incredible complexity and beauty. Some species had evolved shells with chambers that could be filled or emptied with water, allowing them to control their buoyancy with remarkable precision. The largest ammonites of the late Cretaceous had shells over 6 feet in diameter, making them among the largest invertebrates ever to exist. These giants weren't just passive drifters, but active swimmers with jet propulsion systems that allowed them to escape predators or pursue prey with surprising speed and agility. But as impressive as these marine communities were, they were also highly interdependent systems that had taken millions of years to develop. The removal of any key species could trigger cascading effects throughout the entire ecosystem. The specialized feeding relationships, breeding cycles, and migration patterns that characterize these communities made them incredibly efficient, but also potentially vulnerable to rapid environmental changes. As the final hours before impact ticked away, subtle signs of the approaching catastrophe were beginning to appear in Earth's upper atmosphere. The asteroid was now close enough that its gravitational influence was creating minor perturbations in atmospheric circulation patterns. High-altitude clouds were forming unusual formations, and electromagnetic effects were beginning to interfere with the navigation systems of migrating animals. But these effects were far too subtle for any living creature to detect or interpret. The magnetic field fluctuations that might have confused migrating pterosaurs were indistinguishable from normal variations. The atmospheric pressure changes that preceded the impact were too gradual and minor to trigger any survival responses in terrestrial animals. In the coastal regions near what would soon become ground zero for the impact, life continued its normal patterns. Massive herds of hadrosaurs were engaged in their seasonal migrations, following ancient routes that had been used by their ancestors for millions of years. These duck-billed dinosaurs had evolved some of the most sophisticated herd behaviors ever documented, with different age groups and family units occupying specific positions within the migrating masses. The leadership of these herds wasn't determined by size or aggression, but rather by experience and knowledge of migration routes, feeding areas, and seasonal patterns. The oldest individuals, their hollow crests worn smooth by decades of use, served as living libraries of environmental information that was passed down through generations. The communication systems used during these migrations were marvels of biological engineering. Different species of hadrosaurs had evolved distinctly different crest shapes that produced unique acoustic signatures. A trained ear could identify species, age groups, and even individual animals based on the sounds they produced. The cacophony of calls during migration periods would have created one of the most spectacular acoustic experiences in Earth's history. But perhaps most remarkably, evidence suggests that some hadrosaur species had developed primitive forms of musical expression that went beyond simple communication. Fossilized crests show wear patterns that indicate these animals may have engaged in extended vocal performances that served no obvious survival function other than pleasure or social bonding. The predators that followed these migrating herds had their own sophisticated strategies for exploiting this seasonal abundance. Large theropods like Albertosaurus had learned to time their own movements to coincide with the migrations, positioning themselves at river crossings and mountain passes where the herbivores would be most vulnerable. These predatory strategies required not just physical prowess, but also detailed knowledge of prey behavior, seasonal patterns, and landscape features. The most successful predators were those that could anticipate where their quarry would be most vulnerable and position themselves accordingly. This required memory, planning ability, and spatial reasoning that indicated cognitive capabilities far beyond what had previously been attributed to dinosaurs. The smaller predatory dinosaurs had developed their own specialized techniques for exploiting migrating herds. Pack-hunting dromaeosaurids would work together to separate young or injured animals from the protection of the group, then coordinate their attacks with precision that rivaled that of modern wolves or lions. But the migrants weren't defenseless. The adults had evolved protective behaviors that could turn a predator attack into a disaster for the hunters. When threatened, hadrosaur herds could form defensive circles with the most vulnerable individuals protected in the center, while the adults presented a wall of powerful kicks and tail slaps to any approaching threat. The social bonds within these herds were remarkably strong, with evidence suggesting that individuals would risk their own lives to protect others, even when those others weren't direct relatives. This kind of altruistic behavior indicates social sophistication that approaches that of modern elephants or dolphins. As we witness these final scenes of dinosaur life, it's important to remember that we're observing the culmination of 160 million years of evolutionary refinement. Every behavior, every adaptation, every ecological relationship had been tested and perfected over countless generations. The animals living through these final hours represented the absolute peak of reptilian evolution. The asteroid that would end this incredible chapter in Earth's history was now entering the final phase of its approach. In just a few hours, it would strike the shallow seas off the coast of the Yucatan Peninsula with a force that would make every previous natural disaster look insignificant by comparison. The impact would release energy equivalent to over 100 million hydrogen bombs exploding simultaneously, creating temperatures that would exceed those found in the core of the sun. But the immediate destruction, devastating as it would be, would represent only the beginning of the catastrophe. The long-term consequences of the impact would prove even more lethal than the initial blast. triggering a cascade of environmental changes that would make Earth virtually uninhabitable for most large animals. As we prepare to witness this ultimate test of survival, we stand at one of the most dramatic turning points in the history of life on Earth. In just moments, the world that had existed for millions of years would be swept away, replaced by conditions so harsh that only the most adaptable and resilient creatures would survive. The age of dinosaurs, with all its magnificence and complexity, was about to end, not with a gradual decline, but with a catastrophe so sudden and complete that it would reshape the entire future of evolution on our planet. The survivors of this cosmic catastrophe would inherit a world utterly transformed, setting the stage for the rise of mammals and ultimately our own species. The final act of the greatest evolutionary success story in Earth's history was about to begin, and with it would come changes that would echo through the ages, determining the course of life on our planet for millions of years to come. At 11:58 a.m. on that fateful day, the asteroid breached Earth's atmosphere like a cosmic bullet fired from the depths of space. The friction generated by its passage through the upper atmosphere created a fireball brighter than 1,000 suns, visible from hundreds of miles away. But this spectacular light show was merely the prelude to an event that would rewrite the rules of existence on our planet. The creatures below had no frame of reference for what they were witnessing. A family of triceratops grazing near the impact site may have looked up momentarily at the brilliant streak across the sky, their massive three-horned skulls tilting upward in what would be their final moment of curiosity. The light was so intense that it temporarily blinded every creature within a 1,000-mile radius. Yet this was the least of their concerns. As the asteroid plunged through the atmosphere, it compressed the air in front of it to such extreme pressures that the very molecules began to glow. The temperature around the incoming projectile reached levels that existed nowhere else in the solar system except in the hearts of stars. This wasn't just a rock falling from space. It was a cosmic furnace bringing stellar temperatures to Earth's surface. At precisely 11:59 a.m., the asteroid struck the shallow seas off the Yucatan Peninsula with a velocity of 45,000 miles per hour. The impact released energy equivalent to 10 billion atomic bombs detonating simultaneously. In that single instant, more energy was released than in all of human civilization's wars, natural disasters, and industrial activities combined. The asteroid didn't simply hit the Earth, it punched through it like a bullet through paper. In less than a second, it had penetrated 20 miles into the planet's crust, vaporizing everything in its path and creating a cavity that would momentarily reach depths greater than the height of Mount Everest. The temperatures at the impact site exceeded 18,000 degrees Fahrenheit, hot enough to vaporize solid rock and turn seawater into superheated steam. The immediate destruction was beyond comprehension. Every living thing within 600 miles of the impact site was killed instantly, not by the explosion itself, but by the intense heat that preceded it. Dinosaurs, marine reptiles, pterosaurs, and early mammals were flash-cooked where they stood. Forests burst into flame before the shock wave even reached them. The very air itself became a weapon, expanding so rapidly that it created a wall of death racing outward at supersonic speeds. But the asteroid's impact was just the beginning of a cascade of catastrophes that would unfold over the following hours, days, and months. The collision ejected trillions of tons of vaporized rock and debris into the atmosphere. Much of this material was launched with such force that it actually left Earth's atmosphere entirely, creating a temporary ring of debris around our planet. What goes up, however, must come down. Within hours, this debris began raining back down across the entire globe as molten droplets of rock and glass. These weren't gentle meteorite showers, but rather a worldwide firestorm that turned the sky into a furnace. Forests on every continent spontaneously combusted as glowing projectiles heated the atmosphere to temperatures that could ignite even damp vegetation. The mighty Tyrannosaurus rex that had been stalking its prey just hours earlier now found itself in a world transformed beyond recognition. The forest where it had been hunting was now a blazing inferno, the air so hot that each breath seared its lungs. The ground beneath its feet radiated heat like the surface of a stove, while the sky rained fire from above. Even the most perfectly adapted predator in Earth's history was helpless against forces of this magnitude. Across the continent, other dinosaurs were experiencing their own versions of this apocalypse. The great herds of hadrosaurs that had been migrating along ancient routes found themselves trapped in landscapes that had become alien hellscapes. Their sophisticated communication systems, evolved over millions of years, could do nothing to coordinate an escape from destruction that was literally falling from the sky. The marine ecosystem suffered equally catastrophic devastation. The shallow seas where the asteroid had impacted were instantly boiled away, creating steam explosions that could be heard on the opposite side of the planet. Massive mosasaurs, the rulers of Cretaceous oceans, found their aquatic domain transformed into a cauldron of superheated water and toxic gases. The shock waves from the impact traveled through the Earth's crust at speeds of several miles per second, triggering earthquakes that registered magnitudes never before experienced in geological history. These weren't ordinary earthquakes, but rather planet-wide convulsions that caused the ground to ripple like waves on a pond. Mountains crumbled, valleys opened, and entire landscapes were reshaped in minutes. The seismic energy was so intense that it triggered volcanic eruptions on the opposite side of the planet. The massive lava flows in India, which had already been pumping greenhouse gases into the atmosphere for thousands of years, suddenly increased their activity dramatically. This created a feedback loop of destruction, with the impact triggering geological processes that would continue poisoning the environment long after the initial catastrophe had ended. But perhaps the most devastating immediate consequence was the generation of mega tsunamis that raced across ocean basins at jet aircraft speeds. These weren't the relatively modest tsunamis that occasionally devastate coastal regions in modern times, but rather walls of water over 300 feet high that could sweep hundreds of miles inland. A Pachycephalosaurus that had been peacefully foraging near what would one day become the Gulf Coast suddenly found itself facing a liquid mountain racing toward shore at 400 miles per hour. The wave, carrying with it millions of tons of debris, sediment, and the shattered remains of marine ecosystems obliterated everything in its path. Entire dinosaur communities that had existed for millions of years were wiped out in minutes. The tsunamis didn't just destroy coastal areas. They penetrated deep into continental interiors, following river valleys and low-lying areas for hundreds of miles. Fossil evidence shows that marine organisms were deposited in what are now the central plains of North America, testament to the incredible reach of these devastating waves. As the immediate chaos of the first few hours began to subside, the long-term consequences of the impact started to manifest. The massive quantities of dust, ash, and vaporized rock that had been ejected into the atmosphere began to block out the sun. What had started as a day of intense heat and fire was rapidly transforming into a global winter that would persist for months. The skies, which had been brilliant with firelight just hours earlier, now turned an ominous dark gray as particles of pulverized rock created a blanket that encircled the entire planet. The temperature began to plummet as sunlight was blocked from reaching Earth's surface. Within days, temperatures dropped by as much as 50 degrees Fahrenheit in some regions. This sudden climate shift was particularly devastating for the dinosaurs, many of which were already stressed by the volcanic activity that had been ongoing for thousands of years. The great sauropods, which required enormous quantities of vegetation to fuel their massive bodies, found themselves in a world where plants were dying en masse due to lack of sunlight. Photosynthesis, the fundamental process that had powered terrestrial ecosystems for hundreds of millions of years, ground to a halt. Without sunlight, plants couldn't produce the energy they needed to survive. The elaborate food webs that had supported dinosaur communities for millions of years began to collapse from the bottom up. The herbivorous dinosaurs, despite their sophisticated digestive systems and efficient metabolisms, couldn't survive without plant food. The massive herds of triceratops, the duck-billed hadrosaurs, and the armored ankylosaurs began to starve as their food sources disappeared. Their bodies, perfectly adapted for processing vegetation, became liabilities in a world where plants no longer grew. The collapse of herbivore populations had immediate consequences for the predators that depended on them. Tyrannosaurus rex, despite being one of the most formidable predators ever to exist, found itself in a world where prey was becoming increasingly scarce. These apex predators, which had required enormous quantities of meat to fuel their massive bodies, were particularly vulnerable to disruptions in food webs. The smaller predatory dinosaurs fared somewhat better initially, as they could survive on insects, small mammals, and carrion from the mass die-offs. But even these adaptable hunters eventually succumbed as the ecosystem collapse became complete. The sophisticated pack-hunting strategies that had made dromaeosaurids so successful became irrelevant when there was simply nothing left to hunt. In the poisoned skies above, the pterosaurs were facing their own catastrophe. These masters of aerial locomotion found their element transformed into a toxic nightmare. The atmosphere was filled with sulfuric acid droplets that burned their wing membranes and respiratory systems. The air currents they had relied upon for soaring were disrupted by the massive temperature differentials created by the impact. Even the largest pterosaurs, with their incredible wingspans and sophisticated flight adaptations, couldn't survive in skies that had become chemically hostile to life. One by one, these magnificent flying reptiles fell from the poisoned air, ending a lineage that had ruled the skies for over 150 million years. The marine ecosystems, already devastated by the initial impact and tsunamis, continued to deteriorate as acid rain began falling across the globe. The massive quantities of sulfur compounds ejected into the atmosphere by the impact mixed with water vapor to create sulfuric acid that fell like rain across every continent and ocean. This acid rain was far more concentrated than anything in modern environmental disasters. It was strong enough to burn through organic tissues and dissolve the shells of marine organisms. The ocean's chemistry changed so rapidly that many species simply couldn't adapt quickly enough to survive. The great mosasaurs, which had ruled Cretaceous seas with such authority, found their marine domain transformed into an acidic wasteland. The complex food webs that had supported these massive marine predators collapsed as smaller organisms died off in massive numbers. Even creatures that had survived multiple previous extinction events found themselves unable to cope with the rapid pace of environmental change. The ammonites, those beautiful spiral-shelled cephalopods that had been among the most successful marine animals for hundreds of millions of years, finally met their match in the post-impact oceans. Their shells, marvels of natural engineering that had protected them through countless previous crises, dissolved in the acidic waters that now covered much of the planet. As weeks turned to months, the few surviving dinosaurs found themselves in a world that bore no resemblance to the lush, productive ecosystems they had known. The impact winter persisted, with temperatures remaining far below normal as the atmospheric dust blocked incoming solar radiation. The few plants that managed to survive were stunted and nutritionally poor, unable to support large herbivores. Some small dinosaurs may have survived longer than others by adapting their behavior to the new conditions. Evidence suggests that certain species may have entered dormant states similar to hibernation, reducing their metabolic needs during the worst of the crisis. Others may have survived by scavenging the abundant carrion that littered the landscape. But these survival strategies, successful as they may have been in the short term, ultimately proved insufficient. The environmental changes triggered by the asteroid impact were simply too severe and too rapid for most dinosaur species to adapt to successfully. The very characteristics that had made them so successful, their large size, their specialized diets, their dependence on complex ecosystems, became liabilities in the post-impact world. The mammals that had lived in the shadows of the dinosaurs found themselves inheriting a devastated but opportunity-rich world. Their small size, their ability to enter torpor, their omnivorous diets, and their burrowing behaviors had prepared them for exactly this kind of environmental catastrophe. While the dinosaurs starved above ground, many mammals survived in underground burrows, emerging periodically to feed on seeds, insects, and carrion. The birds, being dinosaurs themselves, might seem to have been equally vulnerable to extinction. But the species that survived possessed crucial advantages over their non-flying relatives. Their ability to fly allowed them to travel vast distances in search of food and suitable habitat. Their relatively small size meant they required less food to survive. Most importantly, many early birds retained the ability to enter torpor-like states that reduced their energy requirements during times of environmental stress. As the months passed and the atmospheric dust began to settle, sunlight slowly returned to Earth's surface. But the world that emerged from the impact winter was utterly transformed. The lush forests that had covered much of the planet were gone, replaced by sparse grasslands and scrublands. The complex ecosystems that had supported hundreds of dinosaur species had been simplified to basic communities of survivors. The few dinosaur lineages that had managed to survive the initial catastrophe found themselves in a world that offered little hope for recovery. The environmental conditions that had allowed their ancestors to grow to enormous sizes and develop complex social behaviors no longer existed. The specialized ecological niches that had supported such incredible diversity had been eliminated. One by one, the remaining dinosaur populations dwindled and disappeared. Some may have survived for decades or even centuries after the initial impact, but they were living fossils in a world that had moved beyond them. The age of reptilian dominance was over, and the age of mammals was about to begin. The extinction of the non-avian dinosaurs represents one of the most dramatic turning points in the history of life on Earth. In geological terms, it happened almost instantaneously. A 160 million year success story brought to an end by a single day of cosmic violence. But the consequences of that catastrophic day would echo through deep time, determining the entire future course of evolution on our planet. The mammals that emerged from their burrows in the aftermath of the extinction found themselves in a world of unprecedented opportunity. With the dominant predators and herbivores eliminated, ecological niches that had been closed to them for millions of years were suddenly available. The age of mammals had begun, setting the stage for the eventual evolution of primates, and ultimately our own species. The story of the dinosaurs, from their humble origins as small archosaurs surviving the Permian extinction to their final moments facing cosmic catastrophe, represents one of evolution's greatest success stories. For 160 million years, they had dominated every terrestrial ecosystem on Earth, developing innovations in behavior, physiology, and ecology that pushed the boundaries of what was possible for land-dwelling animals. Their legacy lives on not just in the fossil record, but in the birds that fill our skies today. Living dinosaurs that carry the genetic heritage of their mighty ancestors into the modern world. The next time you see a robin hunting for worms in your garden or watch eagles soaring overhead, remember that you're witnessing the continuation of a story that began nearly 250 million years ago and survived even the most catastrophic day in Earth's history. The age of dinosaurs may have ended, but their story, our story, continues to unfold in ways that those ancient giants could never have imagined. The catastrophe that ended the Cretaceous period didn't just eliminate the dinosaurs, it fundamentally rewrote the rules of life on Earth. As the dust literally began to settle from the asteroid impact, our planet found itself transformed into something that would have been unrecognizable to the magnificent creatures that had ruled it just months before. The immediate aftermath was a world caught between fire and ice. The initial firestorms had consumed vast forests across every continent, leaving behind landscapes of ash and charcoal. But as the debris cloud thickened in the atmosphere, blocking out the sun's rays, these scorched wastelands began to freeze. Temperatures plummeted far below anything the surviving creatures had ever experienced. In this twilight world, where noon looked like midnight and winter never ended, the few remaining large dinosaurs faced challenges that millions of years of evolution hadn't prepared them for. A lone Alamosaurus, one of the last of the giant sauropods, wandered through what had once been a lush forest in what is now New Mexico. The towering trees that had provided its daily sustenance were now blackened stumps, and the ferns and cycads it had depended on had withered and died. This gentle giant, weighing nearly 80 tons and stretching almost 100 feet in length, had been perfectly adapted for a world of abundance. Its massive digestive system required hundreds of pounds of vegetation daily just to maintain basic bodily functions. Its long neck, once an evolutionary masterpiece that allowed it to reach food sources other herbivores couldn't access, had become a liability in a world where there were no tall trees left to browse. The sophisticated herding behaviors that had protected sauropods for millions of years were breaking down as starvation drove desperate individuals to abandon their social groups. The complex communication systems that had coordinated the movements of these massive herds fell silent as one by one the great voices of the Cretaceous were stilled forever. But it wasn't just the giants that were struggling. Even the smaller, more adaptable dinosaurs found themselves facing impossible odds. A pack of Dakotaraptor, those intelligent predators that had once coordinated sophisticated hunting strategies, now wandered aimlessly through the frozen wasteland. Their prey had largely disappeared, and the carrion from the initial die-offs was becoming increasingly scarce and contaminated with toxic compounds from the impact debris. These pack hunters, whose success had depended on their ability to work together, found their social bonds fraying under the stress of constant hunger. The complex vocalizations and body language that had allowed them to coordinate attacks were still intact, but there was nothing left to hunt. Their intelligence, once their greatest asset, now became a curse as they could comprehend the hopelessness of their situation. The skies, once filled with the calls of pterosaurs and the songs of early birds, had fallen largely silent. The great Quetzalcoatlus, those magnificent flying giants with wingspans that rivaled small aircraft, had been among the first casualties of the changing atmosphere. Their massive size, which had once allowed them to soar effortlessly across continents, made them particularly vulnerable to the toxic gases and acid rain that now filled the air. The few pterosaurs that had survived the initial catastrophe found their world transformed in ways that made flight itself deadly. The atmospheric chemistry had changed so dramatically that the very air burned their delicate wing membranes. The thermal currents they had relied upon for soaring had been disrupted by the massive temperature changes, making powered flight exhaustingly difficult. One by one, these masters of the ancient skies fell to earth, their wings folded forever. With them died flying techniques and aerial adaptations that had taken millions of years to perfect. The skies, which had been ruled by reptiles for over 200 million years, were suddenly nearly empty. In the poisoned oceans, the last of the great marine reptiles were facing their own apocalypse. The massive mosasaurs that had ruled Cretaceous seas found their aquatic domain transformed into an acidic nightmare. The impact had not only triggered massive tsunamis, but had also altered the chemistry of seawater itself, making it hostile to most forms of life. These marine giants, some reaching lengths of over 50 feet, had been perfectly adapted to hunt in the warm, productive seas of the Cretaceous. Their streamlined bodies, powerful swimming muscles, and sophisticated sensory systems had made them the undisputed rulers of their domain. But all of these adaptations were useless in waters that had become too acidic to support the complex food webs they depended upon. The collapse of marine ecosystems was particularly devastating because it happened so rapidly. The microscopic organisms that formed the base of oceanic food webs were among the first to succumb to the changed water chemistry. Without these primary producers, the entire marine ecosystem collapsed from the bottom up, leaving even the most powerful predators with nothing to hunt. The few dinosaurs that managed to survive the first year after the impact found themselves in a world that seemed determined to test every possible survival strategy. Some small theropods may have attempted to adapt by changing their diets, scavenging whatever organic matter they could find in the devastated landscape. Others may have tried to enter dormant states, slowing their metabolisms to conserve energy during the worst of the crisis. But these desperate survival strategies, innovative as they may have been, ultimately proved insufficient. The environmental changes triggered by the asteroid impact were simply too severe and too rapid for creatures that had evolved over millions of years in stable, productive ecosystems. The specializations that had made dinosaurs so successful in the Cretaceous world became fatal weaknesses in the post-impact environment. Meanwhile, in underground burrows and hidden refuges across the globe, a very different group of survivors was quietly enduring the catastrophe. The mammals that had lived in the shadows of the dinosaurs for over 100 million years suddenly found their modest adaptations perfectly suited for surviving global catastrophe. Their small size, which had once been a disadvantage in a world of giants, now became their salvation. A shrew-sized mammal required only a fraction of the food needed by even the smallest dinosaurs. Their fur, which had evolved primarily for temperature regulation, provided crucial insulation during the impact winter. Most importantly, their ability to enter torpor allowed them to dramatically reduce their energy requirements when food became scarce. These humble creatures, many no larger than modern mice, possessed behavioral adaptations that proved more valuable than all the sophisticated hunting strategies and defensive mechanisms that had made dinosaurs so successful. Their burrowing abilities protected them from the initial firestorms and the subsequent acid rain. Their omnivorous diets allowed them to survive on seeds, insects, and carrion. when more specialized feeders starved. But perhaps most crucially, many mammalian species had retained the ability to reproduce quickly when conditions improved. Unlike dinosaurs, which often required years to reach reproductive maturity and produced relatively few offspring, mammals could potentially bounce back from population crashes with remarkable speed. The birds that survived the extinction possessed a unique combination of dinosaurian heritage and mammalian-like adaptations. As dinosaurs themselves, they had inherited many of the physiological innovations that had made their group so successful. But their small size, their ability to fly vast distances in search of food, and their capacity for behavioral flexibility gave them advantages that their larger relatives lacked. The early birds that emerged from the extinction bottleneck were very different from their pre-impact ancestors. Many had lost specialized features like elaborate crests or highly specialized feeding adaptations. The survivors were generalists, creatures that could eat a variety of foods, live in different habitats, and adapt their behavior to changing conditions. As the months stretched into years, the impact winter gradually began to ease. The massive quantities of dust and debris in the atmosphere slowly settled back to Earth, allowing increasing amounts of sunlight to reach the surface. But the world that emerged from this prolonged darkness was utterly transformed. The lush forests that had covered much of the planet during the Cretaceous were gone, replaced by simple communities of fast-growing plants that could quickly colonize the devastated landscape. Ferns, which had been relatively minor components of Cretaceous ecosystems, suddenly became dominant as they spread across the ash-covered continents. These hardy plants, with their ability to reproduce through spores and their tolerance for poor soil conditions, were among the first to reclaim the barren landscapes. The complex, multi-layered forest ecosystems that had supported such incredible dinosaur diversity had been simplified to basic communities of survivors. The intricate relationships between plants and their pollinators, the sophisticated food webs that had connected dozens of species, and the stable habitat structures that had persisted for millions of years had all been swept away. In this simplified world, the surviving mammals began their remarkable evolutionary radiation. With the dominant predators and herbivores eliminated, ecological niches that had been closed to them for over 100 million years were suddenly available. Some mammals began experimenting with larger body sizes, filling the roles once occupied by medium-sized dinosaurs. Others developed new feeding strategies, exploiting plant resources that had previously been monopolized by reptilian herbivores. The evolutionary explosion that followed the dinosaur extinction was one of the most rapid and dramatic adaptive radiations in Earth's history. Within just a few million years, the blink of an eye in evolutionary terms, mammals had diversified into forms that would have been unimaginable during the age of dinosaurs. Some lineages took to the trees, developing the grasping hands and enhanced vision that would eventually characterize the primate order. Others returned to the water, beginning the evolutionary journey that would eventually produce whales and dolphins. Still others became large terrestrial herbivores, developing the digestive adaptations necessary to process tough plant materials without the sophisticated gut bacteria that had aided their dinosaurian predecessors. The birds underwent their own dramatic evolutionary expansion, rapidly diversifying into ecological roles that had previously been filled by pterosaurs and small dinosaurs. Some became aerial predators, developing the keen eyesight and powerful talons necessary for hunting from the sky. Others became ground-dwelling herbivores, growing to sizes that rivaled some of the smaller dinosaurs. But perhaps most remarkably, some bird lineages began experimenting with flightlessness, developing into large ground-dwelling forms that could exploit terrestrial resources more efficiently than their flying ancestors. These flightless giants, though they would eventually face their own extinctions, demonstrated the incredible evolutionary potential that the post-dinosaur world had unlocked. The recovery of plant communities was equally dramatic, though it followed very different patterns than the animal recovery. The flowering plants that had revolutionized Cretaceous ecosystems continued their expansion, but they now faced a world with very different selective pressures. The large herbivorous dinosaurs that had shaped plant evolution for millions of years were gone, replaced by much smaller mammalian herbivores with different feeding behaviors and dietary requirements. This change in herbivore pressure led to new evolutionary experiments in plant defense and reproduction. Some plants developed chemical defenses that were specifically targeted at mammalian digestive systems rather than reptilian ones. Others evolved new reproductive strategies that took advantage of the behavioral differences between mammalian and dinosaurian seed dispersers. The insects that had survived the extinction also underwent remarkable evolutionary changes. Many of the specialized relationships between insects and dinosaurs had been severed by the extinction, forcing insect species to develop new ecological partnerships. The coevolution between insects and flowering plants accelerated dramatically, leading to the complex pollination relationships that characterize modern ecosystems. As the early Paleocene epoch unfolded, the pace of evolutionary change began to slow as the new ecosystems stabilized. The dramatic experimental phase that had characterized the immediate post-extinction period gave way to more gradual refinements and specializations. But the fundamental character of life on Earth had been permanently altered. The world that emerged from the Cretaceous-Paleogene extinction was one where warm-blooded creatures dominated terrestrial ecosystems for the first time in over 200 million years. The reptilian solutions to survival challenges that had been perfected over the Mesozoic era had been largely swept away, replaced by mammalian and avian innovations that would define the Cenozoic era. The extinction of the non-avian dinosaurs marked the end of an evolutionary experiment that had lasted longer than any other group of large terrestrial animals. For 160 million years, they had dominated every terrestrial ecosystem on Earth, developing solutions to survival challenges that pushed the boundaries of what was possible for land-dwelling creatures. Their legacy, however, extends far beyond the fossil record. The birds that inherited the post-extinction world carried with them the genetic heritage of their dinosaurian ancestors, ensuring that dinosaur DNA would continue to shape evolution long after the last giant had fallen. The ecosystem structures that dinosaurs had created provided the foundation for the mammalian radiations that followed. Even the climate patterns that had supported dinosaur communities helped shape the environmental conditions that early mammals would exploit. But perhaps most importantly, the dinosaur extinction demonstrated the power of environmental change to reshape the entire course of evolution. The asteroid impact that ended the Mesozoic era was a reminder that even the most successful evolutionary strategies can be rendered obsolete by events beyond the control of any living creature. The mammals and birds that inherited the post-dinosaur world would face their own challenges and opportunities in the millions of years that followed. Some would grow to enormous sizes, rivaling the largest dinosaurs in their ecological impact. Others would develop intelligence levels that surpassed anything achieved during the Mesozoic era. Still others would eventually develop the technological capabilities to leave Earth entirely, carrying life to other worlds. The story that began with small archosaurs surviving the Permian extinction had evolved into something that the first dinosaurs could never have imagined. From the ashes of the greatest mass extinction in Earth's history had emerged creatures capable of understanding their own evolutionary history, of reconstructing the lives of their ancient predecessors, and of contemplating their place in the vast sweep of cosmic time. The age of dinosaurs was over, but their story, transformed and continued through their avian descendants and the mammalian inheritors of their world, would continue to unfold in ways that would have amazed those first small survivors. Emerging from the Triassic deserts, the greatest evolutionary success story in Earth's history had ended, but it had also, in its ending, made possible all the stories that would follow. The final chapter of our journey through deep time brings us to a profound realization about the nature of success and failure in the grand theater of evolution. As we stand in the ruins of the Cretaceous world, surrounded by the scattered remains of the most magnificent creatures ever to walk the earth, we must confront a fundamental truth about life itself. The dinosaurs didn't fail because they were inadequate. They didn't disappear because they were poorly designed or evolutionarily inferior. On the contrary, they vanished precisely because they had become too successful, too specialized, too perfectly adapted to a world that could change in ways they had never encountered before. Think about what we've witnessed in this epic saga. These weren't primitive monsters stumbling through prehistoric landscapes. These were sophisticated biological machines that had solved virtually every challenge that terrestrial life could present. They had conquered the problems of size, developing engineering solutions that allowed land animals to grow larger than anything before or since. They had mastered the complexities of social behavior, creating communication systems and cooperative strategies that rivaled those of modern mammals. Their predatory innovations were masterpieces of evolutionary design. Tyrannosaurus rex possessed sensory systems that could detect prey from miles away, processing power that could calculate attack strategies with computer-like precision, and weapons that could deliver more crushing force than any land predator in Earth's history. Their hunting techniques incorporated elements of patience, strategy, and coordination, that wouldn't look out of place in a nature documentary about modern apex predators. The herbivorous giants had solved equally impressive challenges. Supporting bodies that weighed as much as a dozen elephants required innovations in physiology, behavior, and ecology that pushed biological systems to their absolute limits. These creatures had developed digestive strategies that could extract maximum nutrition from poor quality plant materials, circulatory systems that could pump blood through necks longer than telephone poles, and social behaviors that allowed them to coordinate the movements of herds numbering in the thousands. The flying reptiles had achieved aerial mastery that modern aircraft engineers study with admiration. Pterosaurs like Quetzalcoatlus had solved the fundamental problems of powered flight at scales that challenge our understanding of what's physically possible. Their wing designs, muscle arrangements, and flight control systems represented solutions to aerodynamic challenges that human technology has only recently begun to appreciate. Even the smallest dinosaurs had achieved remarkable sophistication in their own ecological niches. The pack hunting strategies of dromaeosaurids demonstrated cognitive abilities that required memory, planning, and communication skills, approaching those of modern dolphins or elephants. Their use of tools, their capacity for behavioral innovation, and their ability to adapt hunting techniques to different prey species revealed intelligence levels that we're only beginning to understand. But perhaps most remarkably, these creatures had created stable ecosystems that persisted for tens of millions of years. The food webs that supported dinosaur communities were marvels of ecological engineering, with energy flowing through multiple trophic levels with minimal waste. The pollination relationships, seed dispersal networks, and nutrient cycling systems that characterize Mesozoic ecosystems were more complex and efficient than most modern biological communities. This stability wasn't the result of evolutionary stagnation. Dinosaur species continued to evolve, adapt, and diversify throughout their 160 million year reign, but they did so within ecosystem frameworks that provided predictable resources and environmental conditions. This predictability allowed for the kind of extreme specialization that produced the giants and the sophisticated behavioral systems we've explored. And therein lay their ultimate vulnerability. The very specializations that made them so successful in the stable world of the Mesozoic became fatal weaknesses when that world changed overnight. The massive bodies that had been advantages in a world of abundant vegetation became liabilities when plants stopped growing. The sophisticated hunting strategies that had made them supreme predators became irrelevant when there was nothing left to hunt. The asteroid impact didn't just kill individual dinosaurs. It destroyed the environmental conditions that had made their way of life possible. The complex ecosystems that had supported their incredible diversity collapsed so rapidly that even the most adaptable species couldn't adjust quickly enough to survive. This teaches us something profound about the nature of evolutionary success. In biology, as in human affairs, the strategies that make you dominant in stable times can become the very things that destroy you when conditions change unexpectedly. The dinosaur's fate reminds us that even the most perfect adaptations are only perfect for specific circumstances. The creatures that inherited the post-extinction world succeeded not because they were superior to the dinosaurs, but because they possessed characteristics that happened to be useful during a global catastrophe. The small mammals that emerged from underground burrows weren't better designed than Triceratops or Tyrannosaurus rex. They were simply more suited to surviving in a world where being small, unspecialized, and able to eat almost anything had suddenly become more valuable than being large, powerful, and perfectly adapted to specific ecological roles. The birds that survived the extinction carried forward the dinosaurian legacy, but they did so by abandoning many of the specializations that had made their ancestors so impressive. The survivors were generalists, creatures that could adapt their behavior, change their diets, and exploit new opportunities as they arose. This pattern repeats throughout the history of life on Earth. The most successful groups during stable periods are often the most vulnerable during times of rapid change. The trilobites that dominated Paleozoic seas for hundreds of millions of years were swept away by environmental changes they couldn't adapt to quickly enough. The ammonites that had survived multiple previous extinctions finally met their match in the rapidly changing ocean chemistry of the post-impact world. But extinction events, devastating as they are, also create opportunities for evolutionary innovation. The disappearance of the dinosaurs opened ecological niches that had been closed to other groups for over 100 million years. The mammals that had lived in their shadows suddenly found themselves in a world where being small was no longer a disadvantage, where intelligence and behavioral flexibility were more valuable than size and strength. The evolutionary explosion that followed the dinosaur extinction was one of the most rapid and dramatic in Earth's history. Within just a few million years, mammals had diversified into forms that filled ecological roles from tiny insectivores to massive herbivores. Some returned to the oceans, beginning the evolutionary journey that would eventually produce whales and dolphins. Others took to the trees, developing the grasping hands and enhanced vision that would characterize the primate lineage. The speed of this diversification demonstrates the incredible evolutionary potential that had been suppressed by dinosaur dominance. For over 100 million years, mammalian innovation had been constrained by the presence of superior competitors. When those competitors disappeared, evolution exploded in directions that had been impossible during the Mesozoic era. The birds underwent their own remarkable radiation, rapidly expanding into ecological roles that had been filled by pterosaurs and small dinosaurs. Some became aerial predators, others ground-dwelling herbivores, and still others experimented with flightlessness, growing to enormous sizes in the absence of large terrestrial predators. The plants that recolonized the devastated landscapes also underwent dramatic evolutionary changes. The disappearance of large herbivorous dinosaurs altered the selective pressures that had shaped plant evolution for millions of years. New defensive strategies, reproductive mechanisms, and growth forms emerged as plants adapted to a world dominated by very different kinds of herbivores. The insects that survived the extinction found themselves in a world where many of their previous ecological relationships had been severed. The specialized partnerships between insects and dinosaurs were gone, forcing rapid evolutionary experimentation in new directions. The coevolution between insects and flowering plants accelerated dramatically, creating the complex pollination networks that characterize modern ecosystems. As we reach the end of our journey through the age of dinosaurs, we're left with a story that's both tragic and inspiring. Tragic because it represents the loss of creatures so magnificent that they challenge our imagination. The largest land animals that ever lived, the most sophisticated predators, the most complex ecosystems, all swept away in a geological instant. But it's also inspiring because it demonstrates the incredible resilience and creativity of life itself. Even the most devastating catastrophe in Earth's history couldn't extinguish the flame of evolution. From the ashes of the Cretaceous world emerged new forms of life that would eventually surpass even the dinosaurs in their complexity and achievements. The mammals that inherited the post-dinosaur world would eventually produce creatures capable of understanding their own evolutionary history. They would develop technologies that could peer back through deep time to reconstruct the lives of their predecessors. They would gain the ability to leave Earth entirely, carrying life to other worlds in ways that the mightiest dinosaurs could never have imagined. The birds that carry dinosaurian DNA into the modern world continue to amaze us with their intelligence, their beauty, and their incredible diversity. Every time we see an eagle soaring overhead or watch a raven solving complex problems, we're witnessing the continuation of the dinosaur story in forms that have adapted to our modern world. The legacy of the dinosaurs extends far beyond their fossils. They shaped the very structure of terrestrial ecosystems, created the evolutionary pressures that drove mammalian innovation, and demonstrated the heights that biological complexity can achieve given enough time and stable conditions. Their story teaches us that success in evolution, as in life, is always temporary. The strategies that make you dominant today may become your weaknesses tomorrow. But it also shows us that life finds a way to continue to adapt, to explore new possibilities, even in the face of seemingly insurmountable challenges. The dinosaurs ruled the Earth for 160 million years, longer than any other group of large terrestrial animals. During that incredible span of time, they filled every ecological niche, conquered every habitat, and developed solutions to survival challenges that pushed the boundaries of what was possible for living creatures. Their reign ended not with a whimper, but with one of the most dramatic events in the history of our planet. In a single day, cosmic forces beyond their control brought down an empire that had endured for longer than mammals have existed. But in their ending, they made possible all the stories that would follow. As we stand in the modern world, surrounded by the descendants and inheritors of the post-dinosaur Earth, we carry with us the lessons of their incredible journey. We are reminded that no dominance is permanent, that even the most successful adaptations can become vulnerabilities, and that life's greatest achievements often emerge from its greatest disasters. The age of dinosaurs is over, But their story continues in every bird that flies, every mammal that walks the earth, and every human being who looks up at the stars and wonders about our place in the vast sweep of cosmic time. They showed us what life can achieve given enough time and opportunity. Now it's our turn to see how far the story can go. From the first small survivors emerging from the Permian extinction to the final giants falling beneath a rain of cosmic fire, the dinosaurs wrote the greatest chapter in the book of life on Earth. Their story is our story, their legacy our inheritance, and their journey a testament to both the fragility and the incredible resilience of life in our universe. The dinosaurs are gone, but they are not forgotten. In museums around the world, their bones continue to inspire new generations of scientists and dreamers. In laboratories, their DNA, preserved in their bird descendants, continues to reveal secrets about how life adapts and evolves. In our imaginations, they continue to capture our sense of wonder about the incredible diversity and majesty that evolution can produce. This is the complete history of dinosaurs, from their first day to their last, a story of triumph and tragedy, innovation and extinction, dominance and vulnerability. It's a story that reminds us that we, too, are part of an ongoing evolutionary experiment, inheritors of a planet shaped by cosmic forces and biological innovations that stretch back billions of years. The dinosaurs had their day in the sun,